Okay, so we will start the session 2 of calculus, that is differentiation. So last time, yesterday we did limits. If you have any questions on limits, you can ask anytime. Okay, so today we are going to do the usages, the first usage of limits or the calculus, that is differentiation. So another session we are planning to do the integration. Okay, right. So just a recap, we discuss what is mean by calculus. Right, calculus. It's all about when we have indeterminate forms like 0 divided by 0, infinity divided by infinity, infinity minus infinity, and there are some more scenarios like 0 into infinity. So in that kind of scenarios, the concept of limits help us to or provide as a mechanism to find the exact value. So when you get infinity divided by infinity, sometimes the actual result is infinity, sometimes the actual result is 0, sometimes the actual result is something like 1 or maybe 5 by 2. So we discuss those things, right? So you can't say exactly what is the value, it depends on the function that you are working on. Okay, so that is what limits is all about. So we found some techniques also. Sometimes we can factorize and cancel out, sometimes we have to multiply it by the conjugate to get the factors. If it is something to do with the infinity, limits to infinity, we can just divide by the highest uh, power, right? So those three we discussed. We didn't discuss the L'Hopital rule, that we are going to discuss after doing the differentiation. Okay, right, now we are moving to the first usage, that is differentiation. Okay, differentiation, right? So let's move on to the topic. Right, so differentiation is all about, so the term itself, differentiation, right? So the subject is differentiation. So how does the word comes? It comes from the word difference. Difference. And they just made it a noun, right? So from difference, they made another noun called differentiation, right? So difference means the change, right? So differentiation means rate of change, right? So rate of change. So it's all about finding the rate of change, right? So differentiation is all about finding the rate of change. So whenever you hear the word differentiation, we are talking about, or we are trying to find the rate of change of a function, right? Rate of change of function. So so it's very important thing, right? It's very important thing. You have learned in your O level also, rate of change. The most popular concept that you are really familiar about rate of change is the concept of speed or the concept of velocity, right? So of course the speed is a scalar, velocity is the vector, right? So if you consider the direction as well. So what is mean by velocity? So velocity means the rate of change of distance, right? Rate of change of distance. For example, so let's try to understand what is this concept is all about first, right? Before move dig into the how to do differentiation, etc. So when it comes to velocity means rate of change of displacement, right? Displacement. For example, if I say I am now moving at 1 meters per second, right? So assume that I am moving at 1 meters per second, say constant velocity. That means every second I move 1 meter. Every second I move 1 meter. So that is the rate of change. Then you know that if I am moving at 1 meters per second, in 10 seconds I am supposed to move 10 meters. If I am moving at 10 meters per second, in 1 minute, 1 second, of course 10 meters, in 10 seconds, I am supposed to move 100 meters, right? So likewise, once you know the rate of change, you can predict, right? So what is going to happen in a particular time, right? So that is very important when it comes to real world also. We are really interested about rate of change, right? For example, we are interested about the rate of change of the economy or the economic growth. So economic growth means how fast the economy is growing, right? How fast the economy is growing. If you have high, bigger economic growth, that means we are moving very good. The country is moving really good. If the economic growth is negative, that means it's not a growth, right? It's a shrinking, right? Of course, if the economic growth is zero, that means we are neither growing nor shrinking, right? So likewise, that is very important, right? So that is very important not only in normal engineering or whatever, it's even in economics and some other business, right? In almost all areas, this concept of rate of change is really interested. That is why even not only for engineering students, even for students who are working on economics, so they are learning calculus, right? They are learning calculus because when they move on to serious things, they have to understand calculus, even business studies, because it's all about the how rate of the growth of the business, whether it's a growing, whether it's a shrinking. Okay, so likewise, you can see everywhere there are usages. Everywhere there are usages of rate of change, right? So even inflation rate, right? So now we are talking about the rate of change of the spread of coronavirus, right? So these days, likewise, you can see that hundreds and hundreds of thousands of usages are there. That is why a lot of people are interested about calculus, right? So one of the reason is this concept of differentiation. Okay, right. So let's look at some examples. Try to understand this, right? So what you have to do is you have to map, or you have to understand the concept, the real world scenarios, what is mean by the rate of change. Then in maths we like to map it to a mathematical expression, right? So that is how we understand this. Of course, we have a real world scenario, right? Real world scenario. So we have a real world scenario, maybe moving object or whatever. Then we try to map it to a mathematical function, right? Mathematical function, right? It can be something like y equal x, or y equal 3, or y equal x squared. So it can be some weird function, right? So once we map it to the mathematical function, you can look at it or you can plot it. Then you can visualize and understand this. If it is y equal x, we know that the growth is something like this, right? If it is something like y equal 3, we know that it's sort of a constant, it is at 3. If it is y equal x squared, we know that it shrinks like this and then grows like this, right? So it can be even some more and more complicated things. So we look at the real world scenario, whether it's a speed or acceleration or inflation or economic growth or whatever. We try to figure out what is the closest function. Of course, there are techniques to do that that we are not going to cover, right? So by looking at this data, real world data, right, analyzing real world data, there are techniques to find what is the closest function. Then of course we can analyze this function rather than the data. Then using differentiation and those things, we can predict what is going to happen in next 10 years, etc. Okay, so that is very important, right? So especially when it comes to now weather predictions, etc., we heavily use those things because they want to find those things to predict what is going to happen in the next 2 days or next week, right? Within next week. Okay, so that you can see there are a lot of usages when it comes to differentiation, because we are interested about the rate of change, right? So when we have a rate of change, we can predict what is going to happen in next 10 seconds or next 1 day or next day or whatever. Okay, depending on the scenario, right. So that is the idea. So therefore it's very important to have good idea about uh, some mathematical functions and how the shape of that function, right? What is the shape of that function, right? So this is an example for where rate of change is constant. Now you can see that every time, so say this is x-axis, this is y-axis. When x is 0, the y is 4. When x is 1, the y is 4. When x is 2, y is 4. Now you can see whatever the value of x, the y is same. So that means there is the rate there is no rate of change, there is no change actually, because it's always the same value, right? It is always the same value. So it's something like you are moving at 4 meters per second. So at any time your speed is 4 meters per second. That means there is no rate of change in rate of speed. When it comes to your speed is a constant, right? So something like that. Okay, so there is no rate of change, right? There is no rate of change. And now if you think of this as a time, or the time versus velocity, right? If this is your velocity, now you can see that the velocity is not changing, right? Constant velocity. If this is time versus displacement, that means you are at 4 meter displacement, you are keep on in the 4 meter displacement. That means you are not moving, you are say something like this. It's very important to understand these concepts, otherwise you don't appreciate these concepts, actually you don't understand, right? So this is where I am in, so this is where that person is in. So initially we are something like 4 meters away, like 4 meters away, and the time passed by, that person just stay there. That means after 2 seconds also 4 meter, after 4 seconds also 4 meter, if that person is stationary. So this is what we are getting under T and S, displacements versus time. So you can see there is no change, there is no change. That means there is no actually in this case what will happen is the distance is the same. If you go for speed or something, then we say rate of change is 0, because there is no speed, because that person is stationary. That is why it's always 4, always 4. But after sometimes if it is not 4, if it is 5, now all of a sudden here 4, here 5. So he has moved in a constant speed. Okay, so that is how you understand. So the most important thing is, once you understand, of course anyone can remember or memorize saying that, okay, when you differentiate sin x, the value is cos x. When you differentiate ln x, value is 1 over x. So that any fool can do it, any fool, right? So as long as you have memory. But only the people who has that processing power, that attitude, can understand these things and use these concepts to analyze a particular scenario, right? So that is what we need, that is what we need. Okay, right? So that is constant rate of change. So even it can be a 0 rate of change. So then it is not something like this, then it is something like this, right? So in that case we say the rate of change is 0. So here rate of change is a constant value. This is also constant, but it is 0, right? That means the rate of change is 0, right? Rate of change is 0. So likewise, so actually here also rate of change is 0, but the value remain in the constant value. Okay, right? Right. So then if you move on to something like y equal x, something like y equal x, so y equal 2x, then of course you can see that there is it's a constant rate of change. So here not the rate of change is not the constant, here the value is 0, sorry, value is constant, then rate of change is 0. So here what happens, rate of change is 0, right? Rate of change is 0, value is a constant, right? Value is a constant. uh, when it comes to here also, the value is also constant, the rate of change is also rate of change is 0. But if you take something like this, now value is changing, right? So in that case value is changing, now the rate of change is constant, right? Rate of change is constant. For example, if this is time versus displacement, now you can see after 2 seconds displacement is 4. Alright, after maybe 4 seconds displacement is 8. Now you can see it is, but there is a change, but that rate of change is constant. So that is why we get a straight line, right? Straight line, it's a constant rate of change. It's something like that person is moving at a constant speed, right? Constant speed. So this is something like he is coming towards you. So this is he is going out away from you. This is he is coming towards you. Then of course you have he is moving away from the other side. Okay. So still the rate of change is a constant. That is why we have straight line. Right? We have straight line. So always whenever you see a diagram, just see whether it's something like distance versus time or velocity versus time. So if it is a velocity versus time, you are plotting the rate of change graph. If it is something like distance versus time, you are plotting the original quantity. Okay, right. So you have to spend some time to understand these concepts, right? Right. So let's take a practical example. So because I am not in a hurry to go into the differentiation without understanding what is the real use of this. So let's move on to a real world example, because most of the time you are really familiar with this uh, time versus displacement graph. Okay, time versus displacement graph. Let's take something like this, right? So if you understand this, you will really easily you will understand differentiation. Okay, right. So let's take an example. uh, so I will take an example. Assume that uh, this is your time. So this is time, and this is displacement. Right? This is displacement. Now assume that now initially this is the displacement. Now he is just, or that person is just stationed there. So time passed by, but the displacement remain the same. So it's something like this. Uh, so this is where I am in, right? I am in. This is where that person is in. So I am here. That person is somewhere there. Time passed by, but the person remain there. So therefore, the distance is, or the displacement is the same, right? Right. So now, what about the rate of change? Now this is the normal two entities. Now let's plot the uh, rate of change graph. Right? Rate of change graph. So that means I have here the time. I have the time here, right? But now I have not the displacement, I have the velocity, right? Velocity, right? Now what about the graph here? Now you can see actually he is stationary. He is stationary. That person is stationary. That is why the displacement is not changing. So what is the velocity there? The velocity is going to be what? So velocity is going to be 0 and keep on 0. Keep on 0. So the rate of change graph is something like this. I will just draw it in red color, something like this. So this is your displacement versus time. This is your velocity versus time. Velocity remains 0. Velocity remains 0. So that is the first scenario, right? That is the first scenario that you can think of. Okay, that you can think of. Right. Now let's look at another scenario. Uh, so now assume that again it's S versus T. Now that person is moving. Assume that that person is initially at your place, right? Same as your place. Now it's something like this. So okay, so it crash. So there are some bugs in node, one node. So therefore it might get crashed once in a while. Okay, right. So let's get it again. So assume that now he is moving at a constant speed like this. I assume that initially he is near me, right? Near me. And now that is the now you can see gradually he is moving away when the time pass by. Right. So this is the displacement. This is the time. When time passed by, after 1 second, maybe he is 1 meter away. After 2 seconds, maybe 2 meter away, or whatever, right? So this is how it works, right? How it works. Now, what about the rate of change versus time? Now, this is the displacement versus time. Now, let's try to draw the rate of change versus time for this. right? So rate of change means what? Velocity, right? Velocity, right? So let's take it again. This is again time, and this is now velocity. Now we know that by looking at this, we know that he is moving in a constant velocity. Constant velocity. So as in this case, it's something like the velocity is 1, because you can see the gradient is, it's something like 45-degree angle. It looks like velocity is actually 1. So let's take it as 1, because if it is something like this, velocity is bigger than 1. If it is something like this, if it is the angle is less than 45, some velocity is less than 1. Okay, so in this case, the way I draw it, it looks like the velocity is 1. Okay, so anyway, let's draw it like that. So I will take the other ink. So my velocity graph is in red, something like this. Right, now you can see the rate of change has a value. Earlier rate of change is 0, right? When this is something like this, when this is something like this, we have a rate of change value now, right? So it can be 1 or 2 or whatever. For example, if I had something like this, something like this, then the rate of change value is going to be not 1, it's even bigger than that, something like this. Okay, so it must be a straight line, something like this, right? If it is something like this, the rate of change value is going to be lesser but still constant, right? So that is how it works, right? That is how it works. So if you don't understand this, no point learning differentiation, right? Because we are going to predict these things using differentiation, right? So if you don't understand this, no point knowing d by dx sin x is cos x or whatever, right? So that is just a parent, just a parent. Right, now let's look at another scenario. Right, now let's look at another scenario. The third scenario, I'm again drawing a S versus T graph. Right, so let's move on to black. So I'm going to make it a little bit complicated now. Say this is S and T again. Right, now assume that its shape is something like this. He is initially at the place where I am in. Now he is initially moving in a constant speed. Constant speed. Then he is going to now let's let's do something like this. He is initially, he is going to do some acceleration now. So let's do something like that. So he is going to do something like this. He is going to do something like this. Right? Up to this point, right? Then he is going to move in that same speed. It's something like vehicle, right? So when we start the vehicle, you will see that speedometer is getting increased, right? 5, 12, 20, 30, 40. Now assume that once we reach to 40, now he is going to maintain that speed. That means speedometer is not changing, right? It's constantly at 40. Say now you are in a, say something like highway, and now you are moving in the same speed, right? Same speed. Now it's going to be a straight line after this point. So it's going to be in that straight line. Now assume that the person is going to decelerate, right? So he is going to slow down, and he is going to slow down. Then what happens? Then it will be something like this, right? Right. So then it will be something like this. Maybe after slow downing, he has just stopped it. Now time passed by, but no change in the displacement. No change in the displacement. Now if you have this kind of a situation, now you can see this is a curve, not a straight line, right? From here to here also it is a curve, right? It is a curve. Assume that it is a curve, and though you don't see it as a, You may not see it as a clearly as a curve, but assume that it's a curve after this point. Right, after this point, of course, this is another straight line. Right, know how to draw plot the rate of change graph for that. So this is the most important part. Right, now here you can see it's acceleration. Acceleration means rate of change is also increasing. Right, so rate of change is our if it is a vehicle, the rate of change is our speed. Now we can see speed is increasing. Right, so we can see the speedometer. Of course, it is 5, 10, 15. Now it is not a constant speed. It is not a constant speed, but assume that it's a constant acceleration. So in that case, what happens? It will be something like this. It will be something like this up to that point. Right, up to that point, I will just draw some lines here. Okay, now up to this point it's a constant rate of change. Constant rate of change. Now here constant rate of change means the rate of change of speed. Okay, rate of change of the displacement. But here you can see he is just moving in a actually this is acceleration. The rate of change is getting increased, right? Rate of change is getting increased because this is the rate of change, and this is rate of change u versus time. Now because it's acceleration, that rate of change is getting increased but at a constant rate. But here it's moving at a constant speed now, therefore that constant speed is going to be maintained now, right? That constant speed or the velocity is going to be maintained now up to this point. Right, so you can see here it's getting increased but it is now constant. Now here there is a deceleration. Deceleration means now the rate of change is getting lower and lower. Assume that it's at a constant speed. Therefore what is going to happen is, assume that it came into a standstill. It will be something like this. Right, then of course you can see the displacement is not changing. That means it is at a rate of change, or that velocity is now zero. Velocity is now zero. Now the rest of the stuff is going to be something like this. Something like this. And so like that. Let's draw a straight line. Something like this. Okay. So now using this, predicting this is not a big issue. Using this, predicting this is not a big issue. Why? This is straight line. We know that the rate of change is the gradient, right? If it is something like y equal, if it is something like so, uh, if it is something like y equal 3x, we know that this rate of change is 3. Rate of change is 3, right? Because we know that gradient is the rate of change, right? So that is why we call it gradient, right? So if it is y equal 2x, the rate of change is 2. So finding this is not a big issue, right? Now again, assume that this part is y equal 3x, right? Y equal 3x. So we know that this value is 3. So that is not issue, right? Finding this or this shape rate of change is not a big issue, but the issue is when this is a curve, right? When this is a curve like this, you can see at different times the rate of change different, rate of change is different. So that is why we get a different rate of change values, right? Different rate of change values. How to find this value is our challenge. So that is what we are going to discuss under differentiation, right? Here also we have the same challenge because it's a curve, and because it's a curve like this, at different times the rate of change is different. You can see the rate of change is getting different. It's getting lesser and lesser and lesser. Of course ultimately it becomes 0, but how to find this value, whether it's 2.5 or whatever at this particular time, that is what we are going to discuss in differentiation. Of course this curve can be really really weird shape, right? So this curve can be really weird shape, something like something like this can be, this part can be something like uh, something like this, or it can be something like this, and it can be something like this, right? So depending on the shape, this is going to be different, this is going to be different, right? So therefore what we are interested is, given this kind of a curve, how to find the rate of change, right? Of course, if it is something like this, something like this, using conventional mathematical concepts we can find that is why you learn the concept of straight line, y equal mx plus c. But because gradient is the rate of change, right? Here gradient is 0, that is why it is 0. This is right, this is something like y equal 3, where m is 0, right? So something like this. So this is something like y equal 3. Now you can see, if you put it into y equal mx plus c, is something like 0x plus 3. Now you can see rate of change is 0, right? So gradient is 0. This is something like 3x plus 0. Now the rate of change is 3. Even when it is something like y equal 3x plus 5, still the rate of change is 3, right? So rate of change means this angle theta, right? Tan theta, right? But here this angle is going to be change all the time, so that is why we have something like this. And there can be even weird situation, you have a weird curve, this one is also curve. Now this one is also that is possible, right? So it is not that for every curve you are getting a straight line here. Sometimes this is a curve, very weird curve, your rate of change is also a curve now, so that is possible. So those scenarios we are going to discuss, right? So that those are the scenarios that we are going to discuss from this point onward. So I hope you get what we are trying to understand, right? So that is the first thing. So sometime what happens is, after doing the differentiation they haven't understood what they are really doing, right? So they have just memorized few things, right? So don't do like that, okay? So this can be a curve, even the rate of change can be another curve. So but we are going to find how from this curve, how to find this curve. So that is all about differentiation, okay, right? So let's move on to the our note now, right? So our idea or our challenge is, given a curve like this, right? How to find the rate of change at a particular point, right? How to find the rate of change at a particular point. So I will just using some online resources. So I will be giving these links, right, in your WhatsApp group, and also in the video I will be giving these links that I am using in this session, right? So something like this. Say assume that our graph is something like this. In this case it is y equal x squared, right? But it can be anything. Now if I want to find the rate of change at this point, okay, so it is the tangent at that point, tangent, okay. So it is if I want to find the rate of change at this point, right? So if I want to find the rate of change at this point, it's going to be tangent, and assume that I want it here, it is going to be, so this is the point I am interested, so it is going to be a tangent at that point, something like this, right? So I will make it a little bit thinner. So this is the point I am interested, it's going to be something like this, something like this. So we want to find this angle, this theta, right? This angle theta. So that is what we are interested, that is what we are interested, okay. So if it is something some other point, not that point, some other point, say somewhere like this, somewhere like this. So its most important thing is understand this, what is what you are going to do, somewhere like this. Now the rate of change is not here, the value of this one, because now it's even steeper, it's something like this straight line, so I have to draw it properly. So what I'm going to do is, I'm going to use the tool rather than me drawing this, right? So let's move into the tool. Say assume that I want to find the rate of change here, right? Rate of change here. What I need is something like this, So I want the rate of change in this point. So right, so this is what I really need. So I want what is the gradient of this, sorry, what is the gradient of this tangent. So this is called the tangent, right? So that is how the word tan came for the trigonometry also, the term tan. So it comes from the tangent. So tangent, so what I need is this particular angle now, because I am interested about the rate of change at this point. At this point, what I really interested is what is this angle, right? What is this angle? Oh, the tangent means basically radian means the tan alpha. Tan alpha. So you can see this is the angle. So if I can find this tan value, I know the rate of change at this point, right? I know the rate of change at this point, but that rate of change is going to be different from the rate of change at a different point. For example, assume that uh, I want to find the rate of change not at this point. I want to find the rate of change at this particular point, right? This particular point. Now you can see it's even steeper. So what I have to do is, so I have to move this somewhere here. Then I want to take it somewhere here. Okay, this is that is now you can see that angle is different. So now the rate of change is even bigger, right? So if I want to find the rate of change here at this point, so what I want to do is, so at 2, right? At 2, it is going to be something like this, a little bit lesser, right? So something like this. Now you can see it's changing, right? This one is getting all the time, it's getting changed, right? It's all the time it is getting changed, because when I move it, you can see the rate of that tangent's slope is keep on changing. So you can see different slope. If I go somewhere here, its slope is even other way now, right? Now the slope is something like this, right? Now the slope is something like this, right? Right, so we want to find out what is this gradient for the tan theta value for different places. So that is all about what we are interested. Okay, so it can be even a very complex curve. Still, using differentiation, we can find the value. Okay, right. So that is what we are interested. So remember, when we say calculus, another name we gave to calculus is, in the last session we discussed, infinitesimal calculus, right? Infinitesimal calculus. So the short term is name is calculus, the long name is infinitesimal calculus. So what is mean by infinitesimal? Very small value, right? How small? Very small. You can't even quantify. So that is why we said when it comes to calculus, we are talking about small and smaller values, and we are going to build a concept using that the concept of infinitesimal. Okay, right? So we are going to do the same thing here, right? Right. So now again, let's move to somewhere like point somewhere like here. Okay, so I'm moving this somewhere here. So I am interested about the gradient at 4, right? So that means I am interested about finding this, right? The gradient of the tangent, right? So that is the rate of change there. But you can see straight away we can't find that. But what we can do is, I will do something like this. So I will just zoom it, right? So I am interested about point 4, okay, x value 4, okay. So that means this, that means I am really interested about finding this tangent value, gradient of this line. But rather than finding that, what I'm going to do is I am going to do something like this. So I'm going to keep this p value here. I'm interested about here, this value somewhere here, right? So somewhere here, but I am interested about the value here, right? I'm interested about the tangent here, but I don't since I don't have a mechanism to do that, so let's make p somewhere here. Okay, so now my q point is here, p point is here. Now I know that at that point this is 30, at this point it's somewhere like 5 or whatever, right? At 2, right? At 2 I have the value of this one. At, say, this is something like, say, 5 point something, I have the value, right? So now you can see this gradient is somewhat closer to that particular gradient, right? Right, so that particular gradient is gradient here, which is somewhere like here, but it is this one and that one is not the same, but these two have somewhat differences, or somewhat closer to the value, but there is a error. So let's see how to minimize that error, right? How to minimize that error, right? So this is the scenario that I just demonstrated there. So I want to find the gradient at x naught or that p naught pi. So rather than finding the gradient at that one, what we have done is we have find a point in the graph in p naught, right? P naught. So I'm interested about the tangent, but since I can't figure out how to draw the tangent, I draw a straight line from P naught to, I found another point in the graph at x equal x naught plus delta x. So delta x means very small value, right? So in mathematics, we use delta to represent very small value, that infinitesimal value. So how small? Very, 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 very small. But when we draw it, we just exaggerate and show it. But we are going to make it close and closer to the zero. Okay. Now you can see this gradient of this green line is not the same as the gradient of the tangent at p naught. Right. Of the gradient of the tangent at p naught is going to be something like, or the tangent is going to be something like this. Right, something like this. Of course, it has to touch it, but you can see this gradient and this gradient is different, right? Different, but you can see it's somewhat closer, right? Somewhat closer. This gradient I can written as, because I am interested about the tan theta value, right? Tan theta value, that is delta y divided by delta x, right? That is the gradient of this green line, right? So I am interested in the tangent at p naught, right? I know that those two are two different, but somewhat closer. So for the time being, let's write the gradient of this line, that is delta y divided by delta x. Okay. So if this is some function is fx, we know that at x naught this height is fx naught. Now this is x naught plus delta x. So delta x is an infinitesimal small value. So therefore this height is f x naught plus delta x, because this is function is fx, right? This is fx naught. This height is fx naught plus delta x, because the value is x naught plus delta x. Now I can find this delta y as, right, f x naught plus delta x minus fx naught, because this height is, right. So let's write it. So I will just zoom it little bit lesser. Okay, right. Now you know that this delta y value, I can write it as f x naught plus delta x. That is the total height. That now I have to subtract this minus f x naught. Right. Now what I need is this, whatever the tangent of this green line, which is going to be somewhat closer to the tangent at this point, right? So that I can write it as whatever the tan. So assume that this is psi or whatever, right? That tan psi equal delta y divided by delta x. Delta y divided by delta x. That is f x naught plus delta x minus f x naught divided by delta x. So because this portion is delta x. Okay, so that's it. But we know that there is a error portion there, because reality it is going to be something like this, because there is a small error here, right? So I will just explain it properly. So this one shows the error properly. Now you can see, so this one is a better diagram. Now what I need is gradient of this, or this orange line, that is the tangent. But what I got is the gradient of this pink line, that is my delta y by delta x, which one, this one. But it has an error. What is that error? The error is this amount. So this amount of error is there, right? This amount of error is there. So you can see the error now, because it is not the tangent we are now talking. So this amount of error is there. This amount of error is there. So what happens is, if you make this delta x smaller and smaller and smaller, right? That means this point is getting closer and closer to the x naught, right? What happens is this error is going to be lesser and lesser and lesser. So that means this error is going to be shrink, right? The more you make delta x smaller or close to the zero, this error is going to be lesser and lesser and lesser. So how do you write that? Right. So in limit notation, right, now we are moving to the limits. In limit notation, we are not making delta x zero. What we do? We make delta x closer to the zero, or we want to limit delta x to zero. So that is the notation we discussed in the last session. Now I can write it as something like this. So what I need is not delta y by delta x, because there is error, right? So this particular error is there. What I want to do is limit when delta x is getting closer and closer to the zero, this one, because then I know that in that case, this when delta x is getting closer and closer to zero, I know that this pink line becomes or getting closer to the orange line. So that is what I need. That is what I need. Okay, what orange or red or whatever. So it is now all of a sudden when delta x is getting closer to the zero, this pink line becomes the orange line. That is what I need, the tangent to the gradient of the tangent at x naught, right? So now we can see I can take the limit for this one. Limit delta x tend to 0 f x naught plus delta x minus f x naught, that is this distance, entire height minus this side, that is this one. But this error is going to be lesser and lesser when delta x is going to be close and close to the zero, right? So you have to understand this. If you don't understand it, again think, right? Because this is something anyone can understand, right? Anyone can understand. Okay, right? And we call this the derivative or the differentiation of fx, right? We just give it a name, right? This particular value, this limit, right? So fx naught plus delta x minus fx naught divided by delta x, because we know that when we take the limit of that getting delta x closer to 0, it is going to be the gradient of the tangent, or the tan value of the tangent, right? So therefore we give it a name, the derivative of the function, because it can be any, this p naught I can take from anywhere, the concept is going to be the same, right? So then we give it a notation, right? Mathematician gave it a notation. So if it is y equal fx, sorry, y equal, so whatever the function, we just call it y dash. If it is fx, we just call it f dash x. Sometimes we just say f dash. If it is y equal something, right, y equal x squared plus 2, then we just call it dy by dx, or we can just call it d by dx fx, or we can just call it d by dx f, or sometimes we just call it capital dxy. So those are just notations, right? Don't get scared. It's something like we write x to the something like, when we have, we have so many notations, right? When we have something like x into x 3 times, we just write it x to the power 3. So it's a notation, right? So you don't get scared by this. When we have something like n into n minus 1 into n minus 2 into up to 1, we just call it factorial. So similarly, this limit, we just write it as either f dash x, or d by dx fx, or d by dx f, or dxy. So this is just notation. The real idea is this limit. So we just need a notation. So unfortunately, it is not just one notation. Different mathematicians came up with different notations, right? So different mathematicians came up with different notations, but all these notations represent this particular limit. Okay, this particular limit. Okay, so that is the most important thing to understand. Okay, and this limit gives the rate of change, right? When the delta x is getting closer and closer to 0, this error is going to vanish. This error is going to vanish. Okay, right? So let's move on. Right, so this is the definition of differentiation or derivative. Given the function fx, the derivative of the function given by f dash x, or d by dx f, or whatever these notations, which itself is a function, it is also going to be a function, is the function of the tangent at given x value. So that is very important. So this derivative is going to give you, if this is your function, right, your derivative is going to give you the function, this function, right? When this is your functions, your derivative is going to give you this function, right? When your function is something like this, your derivative is going to give you this function. So that is what we need, right? That is what we need, right? So let's move on. So first thing what we are going to do is, we want to find out some derivatives using that first principle or the original principle. Original principle means this theory part, because this is the definition, and this is the definition. So if you can find some derivatives of well-known functions using this principle, it will really going to boost your confidence about understanding of the derivative, right? So it's all about understanding, confidence, right? It's nothing to do with the memorizing. So memorizing is going to stop at the end of your exam, right? When you get a come out of the exam hall, your calculus knowledge is over, right? So it's actually waste of your time, right? Waste of your time. If that is the case, you want to keep it forever, right? Then only you have a very good idea about the rate of change when you are living in the society, when you're solving a real world problem, right? Like economic problem or whatever. Then you have that in your so that is where the real professionals are, right? The real professionals have that concepts in their blood. Okay, so they don't just do it for exam. So that is actually waste of time, right? So actually don't do that, right? You are wasting your life, right? Right. So therefore it's very important to do few examples, try to find out this rate of change function using the first principle. First principle means by applying this concept, right? Applying this concept and the calculus in a raw way. Okay, so let's take few examples. Remember, this is our definition. F dash x, so the rate of change function is given by this limit delta x tend to 0, fx plus delta x minus fx divided by delta x, right? So whenever you see this definition, you must be able to visualize this graph, right? This is fx plus delta x minus fx, this is delta x. Of course I can divide this by this, but there is an error. To reduce the error, I want to make the delta x closer and closer to 0, right? So whenever you see this formula, you have to visualize this, and whenever you see this graph, you should be able to derive this formula, because that is not that is not rocket science, right? So that is just common sense, right? Common sense, right? Okay, so no one can say I can't understand this, right? So that means you are right, so your mind is out of control, right? Okay, so let's take some example. Let's take the simplest one, that is assume that your function is a constant function. It is something like this. Your function is constant, right? Your function is constant, and of course we know that when the function is constant, like y equal 3 or whatever, we know that rate of change is what? 0. So that is in reality we know that when this is not changing, that means there is no rate of change. Of course we know the answer is going to be 0. Now let's see whether it is going to be the case by applying this definition. Okay, right, right. So it's something like this now. uh, right. So now our function is something like this. This is my x-axis, this is my y-axis. Now my function is what? Fx equals c. Now assume that c is a positive value, otherwise I will go like this, negative. Assume it's a positive value, it's a constant. Constant means when x changes, fx remains the c, right? Fx remains c, right? This is fx equal c. Now what I want to find is rate of change at a particular value point, right? Somewhere like this. What is the rate of change? What is the rate of change, right? What is the rate of change, right? Of course we know that there is no, the rate of change is 0, because you can see everywhere it is a constant. But let's try to apply to this definition and see whether we are getting that 0. So what we expect is f dash x to be 0, because there is no rate of change, because it's keep remaining in the c value. There is no rate of change of when the time or the x pass by, there is no rate, right? It's same. But let's see, let's apply this and see whether we get the value of 0. Now remember, what is the definition? The definition is going, this is going to give you at any general point what is the rate of change. At any general point what is the rate of change. Okay, so let's apply the definition. So the f dash x is limit when delta x is reached into 0, fx plus delta x minus fx divided by delta x. So that is the definition. Now let's apply it to the fx equals c. Now when fx equals c, obviously fx is going to be what? So whatever the value of x, it is going to be c. Therefore fx is going to be c. That is understood. You can understand. Okay, then what about x plus delta x? Now if it is x, if I have another delta x added, what is the value of this? Of course if it is a constant function, whatever the value, whether it's x or x plus delta x or whatever, the value is going to be what? C. That is why we say it's a constant function, right? So therefore, if x plus delta x is also going to be what? C, because it's a constant function. It doesn't matter whether it's x or x plus delta x or whatever, it's going to be C. Now you can see this is C, this is also C. Now we want to divide it by delta x. Right? In that case, C minus C divided by delta x. Right? C minus D. Of course, we are in a limit. We want to make delta x closer and closer to 0 later. Right? Now, when C minus C, of course, C has nothing to do with delta x. Therefore, I can just C minus C is 0. It's 0 divided by delta x. Right? 0 divided by delta x. Now, if I apply delta x equals 0, what happens? If I just apply delta x equals 0, now it becomes 0 divided by 0, because when delta x is 0, it is 0 divided by 0, right? But I am not interested now. In that case, 0 divided by 0 is an indeterminate form. Remember, 0 divided by 0, infinity divided by infinity, 0 into infinity, infinity minus infinity, those are indeterminate form. Now I have a situation where it's going to be indeterminate form. But again, we are not interested about delta x equals 0. What we are interested is delta x closer to the 0. Therefore, I can just write it. So remember, we did that in the limit section. We can say delta x is not equal to 0. As long as delta x is not equal to 0, this is something like 0 divided by something, right? Because it is something, not 0, right? We are interested about infinitesimal value, not 0, right? Therefore, it is 0 divided by something is 0, because delta x is not equal to 0, right? We are just finding out what happens when it is closer to 0. Therefore, 0 divided by something is 0, that we discussed in the last session. Therefore, now the limit become limit delta x reach to 0, 0. Of course, if when it is 0, it doesn't matter whether delta x is reached to whatever, it is going to be 0. So the answer is 0, right? So at first it might look little bit weird, right? But this is this is 100% logical scenario, 100% logical scenario. So what we got is 0. Now when you do the next example, you will get it more and more familiar with this concept. Of course, this is the concept of limit, right? The concept of limit. Now let's say, so therefore we found that if fx is c, the f dash x is 0. So that is where you found your first derivative. That is, we say that d by dx, right? If something like if fx is constant or c or k, we say that f dash x is equal 0. In other terms, we can say d by dx fx, which is c, equals 0. That is the first derivative you have to remember. When you have constant function, its derivative is 0. Its derivative is 0. So we found it in the first principle. Yes, its derivative is going to be 0. So that is where you get this. Actually, what we have covered is this particular scenario. When you have constant function, right, y equal 3 or y equal 5 or y equal minus 2 or whatever, y equal k, your rate of change is going to be 0, right? So you can see that derivative theory is mapping to the reality, right? Mapping to the reality, right? Now let's take another example, right? So we are going to do few derivatives using first principle. Now assume that it is fx equal x, right? Fx equal x. Now not constant. Fx is x. Now let's draw it again. So I am interested about you understand the subject. I am not interested about you passing the exam, because you know that that is a waste of time if you don't understand. Right? If it is y equal x, it's something like this. Something like this. Okay, so I will do it in one note thing. So I will add another one. new page, right? Say now it is, let's do it. Okay, now assume that our function is y equal x function. Okay, y equal x function, that's something like this, y equal x function. So this is x, this is y, this is y equal x. Okay, right. So now let's write the, now I what I want is rate of change at a particular point, rate of change at particular point. And of course we know that the rate of change is going to be 1 because this angle is 45, right? We know that tan 45 is, tan 45 is 1. That is from your trigonometry knowledge. So in the very first session I told that if you have, we need your knowledge on trigonometry basic functions, right, the concepts like logarithms, to better understand this, otherwise you are going to lose it. Okay, that is why we did those things in your other semesters, previous semesters. Now let's apply the definition. Now our fx is, now this is our fx is x, right? So now let's apply the definition. Limit when delta x is going to be 0, you can do this, so no issue, you can do this, right? So by definition, that is f x naught or fx plus delta x minus fx or fx naught divided by delta x. Now in our case, fx is what? X. Fx is y equal x. Fx is x now. Now let's apply it. Limit delta x tend to 0. Now if now x I to x I want to apply what? X plus delta x. Now rather than x naught, we will just call it x plus delta x. Now it's therefore it's going to be what? X plus delta x, because when x is x plus delta x, the y is also x plus delta x, right? So that is this one minus fx. So we know that fx is what? X divided by delta x. Right. Now if I just apply delta x equals 0, what happens? This becomes 0, then x minus x become 0, and delta x when 0 is 0 divided by 0. Now still I can't just substitute, right? Remember, the first thing you want to, when you are finding a limit, first thing you want to do is just substitute and see whether you can find the value. If I get, when I just put delta x equals 0, if I get something like 2 by 3 or whatever, I am done. But when I just say delta x equals 0, it becomes x plus uh, 0 minus x divided by 0. Now x minus x is cancel out, 0 divided by 0, therefore I can't do that. I can't do that, right? So I have to uh, do something else. So what I'm going to do is, I'm not going to substitute right now. What I'm going to say is, I'm just going to make it cancel out, because x minus x can cancel out. Now it becomes limit delta x tend to 0, and now it is delta x divided by delta x, right? Delta x divided by delta x. Now if I again apply delta x equals 0, it will become what? 0 divided by 0, right? It again becomes 0 divided by 0, therefore we are not yet done. Remember the second technique. So first technique said in limit just apply and see whether you get a value. No, so second technique said if there are common factors, just cancel out, then see whether you can do it. Of course you can see there's a common factor, delta x is a common factor, right? Delta x is a common factor, therefore I can just cancel it out, right? So therefore I can just cancel it out. But remember, you can't cancel it out when delta x is 0. So what we are interested is not delta x equals 0, we are interested delta x is closer to 0, therefore I can say that delta x is not equal to 0. That is why I cancel it out, otherwise it's 0 divided by 0. Now it becomes limit delta x tend to 0 1, because delta x to delta x is cancelled out, that is 1. Now of course when delta x is getting closer to 0, it doesn't matter, what I have is a constant, the value is 1, right? Value is 1. So that is exactly what I want to get. Actually not because I want to get it, I got it. Using this concept of limit, I get 1. Of course, yes, the rate of change is going to be 1 when we have y equal x, right? Because tan 45 equal 1, right? Tan 45 equal 1. That is the scenario we covered here, right? Covered here. Of course, that is 3. If it is 45, this is going to be 1, right? This is going to be 1. Okay. So what you have to do is, now look at something like what happens if it is something like y equal not x, y equal 3x, right? Y equal 3x, then what happens? This is going to be 3 times x plus delta x, right? So this is going to be 3 plus x time, this is going to be, so let's take the pen, 3 times x plus delta x minus 3x, then 3x minus 3x cancel out, it will be 3 delta x by delta x to delta x cancel out, now it will become 3, it will become 3, right? So that is exactly what is going to happen. If it is even steeper, like y equal 3x, your this graph is going to have not from 1, it's from 3, right? It's from 3. Okay, so you can see that the things are going to be comply with the real world scenario, right? So let's take one more example, right? So likewise, you can do few examples. I have given you few examples that you have to try out, that time is really worth, right? Right, so let's add one more. Right, so let's see, I have uh, something like y equal x squared, right? Y equal x squared. uh, in that case, in that case so it's something, it's going to be this x, y, it's going to be something like this. I'm really terrible at drawing things. I think I have to come here, control reset, something like this. Okay, so it must be a curve, right? Okay, so now what I want is, assume that this is y equal x squared, y equal x squared. I want to find a function where it gives, and it gives this tangent value, right? This tangent value, this tangent value. So let's use the first principle again. By definition, the dy by dx. So if dash x equal limit delta x tend to 0, f x plus delta x minus fx divided by, you really have to do this if you want to understand, right? So that is by definition. So it is going to give me the rate of change function. So let's apply. Now my function is x squared. Therefore, when I apply x plus delta x, it's going to be still the limit will be there. Limit delta x tend to 0, x plus delta x squared, because my fx is now x squared, right? Minus fx is now with just x squared, right? X squared divided by delta x, right? Now if I apply delta x 0 again, now this becomes 0, that means x squared minus x squared is 0, this is 0, 0 divided by 0, no, it's not going to work. So therefore I have to do some further simplification. So let's keep on simplifying. Limit delta x tend to 0. Now let's expand this. X squared minus 2 times x times delta x, right, plus delta x squared minus x squared divided by delta x. Now I can cancel out x squared and x squared, right? So if I apply delta x again 0, what will happen? 2x times 0 is 0, this one is 0, 0 plus 0 is 0 divided by 0, still it is 0 divided by 0, right? So therefore still I can't do whatever, right? I really like to do it very fast, but still I am in 0 divided by 0. So now what is the next step? See whether we have factorization. Of course you can see delta x is common now, right? So it happens. Limit delta x tend to 0, Now I'm taking delta x as a common factor. Remember, the second technique says try to find out any common factors, right? Of course delta x is common. Then 2x plus delta x divided by delta x. Now I can just cut it saying that delta x is not equal to 0. We are only interested about the limit, right? We are only interested about the limit. Now it becomes limit, right? I just wonder how to get it back. Vanish. Right, so get it something like this. Right, so I got it something like this. So then so I'm taking the pen again. So now I can delta x to delta x, I can cancel it because I can say that delta x is not equal to 0. Then it becomes limit delta x tend to 0, 2x plus delta x. Now I am okay. If I just apply delta x equals 0, now it becomes what? 2x. Now I got the answer as f dash x equal 2x. F dash x equal to x. Now we say that when you derive or the differentiation of x squared is 2x, that is how we get it. That is how we get it. The differentiation of x squared is 2x. So as exercise, you can do these kind of things. Y equal x plus 5. Do this, apply this and find out what is the value of it. Okay. So another one, y equal x squared plus 2. Y equal x cube. Of course you must know how to expand the cube value, right? So that is something like x into x plus a cube is x plus a into, or we can say x cube 3a squared x plus, right? Likewise you know how to expand the cube value, then all those values will cancel out and you can cut the delta x also. You will get a value like derivative of x cube as 3x squared. So that is another exercise you have to do, right? So do these things at home after the session, so that will really boost your confidence. Once you understand it, you are not going to lose it, right? So that confidence you are going to retain for your entire life. Okay, so do these things like this, you will get some values. Then so today we are going to do the well-known derivatives. Then you will find that okay, I am getting those well-known derivatives, right? I am getting, so I just these three examples. So you have to do these kind of examples. I have given you some examples. Of course there are so many examples when you go to the internet, YouTube, people have done. So you can understand any of these. As long as you understand that, you just apply those three techniques as it is. Apply the limit and see whether you get a value, nothing other than 0 divided by infinity. Then try to factorize, right? Try to multiply it by conjugate, right? If it is, or anyway, this is something to do with this 0, therefore you don't have to divide it by the highest factor, because this limit is the limit related to the derivative is nothing to do with the infinity, right? So therefore you have to apply the first technique or the second technique, right? You don't have to apply the third technique. By using those two techniques you can find these derivatives. Of course there are some complex derivatives, you have to use some other techniques, but these examples, do these things, then you will find that okay, so I can understand what is mean, I can get those derivatives by myself. So then that is not going to be a magic for you. Okay, otherwise when I say derivative of x squared is 2x, just you have to memorize, right? It's actually you are in a really upset mood because you are memorizing something you have not you have no idea how they get it, but this is how you get it. This is how you get it. Okay, right, so let's move on. Right, so it's very important doing these exercises. Okay, so and see whether you can get it. Anyway, my handwriting is really bad, so you have a nice note here, right? That I have uploaded, right? X squared, right? So something like this, you can see that ultimately you get into something like this. We say that 3x squared plus 2x, the derivative is 6x plus 2, right? So first principle, right? First principle. Then of course using the rules also you will find that okay, 3x squared plus 2x, when we differentiate, what we get is 6x plus 2. Okay, 6x plus 2. Okay, so I have given a lot of examples because it is very important to get this into your brain. Okay, brain, not to mind, right? Not to memory, right? Now let's try to understand the meaning of this function. Now remember, when we differentiate something like y equal x, what we get as dy by dx. So f dash x is 1. When you differentiate y equal x squared, what we get is as dy by dx. So d by dx x squared is 2x, right? When we have something like y equals c, what we get as dy by dx is 0. So now let's dig it out and see. Of course, you know that that is going to be the rate of change function. Now let's see whether that is the case. Okay. So let's take few examples to understand it. Right. So what I'm going to do is I'm going to use this interactive tool from the MathIsFun site. So I will give you the link below. So I hope you are following me. Right. So I'm referring to the MathIsFun site. Now let's say I will give you the link. So assume that our function is something like y equal 4, y equal 5. Right. So let's tab it. Now you can see it is y equal, so where is y equal 5? Okay, so I will just make it a little bit smaller so that I can see it. Say y equal 2. Right, this is my fx graph. Now close look at this. This is my fx graph, right? You can see the rate of change is going to be everywhere what? 0, right? So there is no rate of change because it's all the time it is 2. All the time it is 2. We are not going to get a rate of change. We are not going to get a rate of change for this function, right? Now our theory says uh, d by dx, right? So our theory says uh, d by dx of a constant is 0. Of course, c2 is a constant. Therefore, d by dx 2 is going to be 0, right? So what does it means? So that is what we got from the first principle. D by dx is 0. Now of course that is going to be the case because at this point the rate of change is 0. Rate of change is 0. Rate of change is 0. Therefore that is perfectly okay, right? So that is why we got something like this as the rate of change curve. What we got is your gx is basically gx is 0. That is actually you can't see it because the line is in the x-axis. This is your gx, right? This is your gx or the f dash x, right? So f dash x, so let's call it f dash x, right? So this is your f dash x. F dash x, you can't see it because it's in the x-axis. Okay, it's in the x-axis, right? So that is how you understand it if it is something like a constant, right? Of course that gives you the rate of change because everywhere rate of change is 0, right? Now let's take another example. So this is the most important thing I am doing now. Assume that it is y equal x, right? So now we know that our fx is something like this. Now what is the dy by dx we got for x? Remember we did that using the first principle. So when y equal x, what we got is 1, right? When y equal x, what we got is 1, right? So let's see. Now what is the derivative, the rate of change here? That is the tangent. So tangent itself is the same line, because if I draw a tangent at this point, that tangent is also going to be this line, and its tangent is going to be the gradient. So gradient is when it is 4, it is 4. When it is 2, it is 2. You know that the gradient is, for this one, the gradient is something like this. Right? For example, so the gradient is 2 divided by 2. 2 divided by 2 is 1, or 4 divided by 4. That is 1. We know that the gradient of this one is 1. Therefore, of course, when we say d by dx x equal 1, that is perfectly okay. Why? Our gradient is at any time, gradient is also 1. Gradient is also 1. Therefore, we say that d by dx x is 1. Right? D by dx x is 1. That is perfectly valid. Perfectly valid with the reality. Right? So that is why we get it as 1. Right? We get it as 1. So now let's look at it again. You can see when, now closely look at it, at this point rate of change is, now I will just make it little bit bigger. Right, now you can see it down. This is the x-axis. Now this is the rate of change function, or the 1, y equal 1, or this is something like this. So this is my fx, this is my fx, and this red line is my f dash x. So my fx is what? X. My f dash x is what? 1. Why? D by dx x equal 1. That is what we got from the first principle, right? So therefore, this d by dx x is called f dash x, right? F dash x. So here we found that when fx is x, our f dash x is 1. Yes, that is correct, right? So at this point, now I'm right. So at this point, what is the rate of change? 1. Of course, it says 1. Right? At this point, 1. At this point, 1. So everywhere, you look at the two cursors, everywhere my rate of change is a constant value called 1. Right? Constant value called 1. So therefore, my derivative is a, it's giving me the correct value. Right? So it's giving me the correct value. Now let's change it to something like this. Now assume that I have not x, I have 2x, right? 2x. Now my rate of change function is not 1, my rate of change function is y equal 2, right? Now because it's steeper, now it is steeper, but it is the same, right? Everywhere the value is the same, everywhere value is the same, right? Everywhere value is the same, right? But it's a constant. Now if I make it something like 0.5x, right? Now it's less steeper, but the rate of change is 0.5 everywhere, right? So likewise, now let's do something like this: y equal x plus 2. Now you know that y equal x plus 2 graph is the gradient of it. The y equal x plus 2 is also 1, right? So that is also 1, right? Because it's parallel to the y equal x graph. Now you can see the rate of change is still 1. Rate of change is still 1, right? So that is perfectly okay, because it's parallel to the y equal x line. Therefore, what I got to get, what I am supposed to get as the derivative of x plus 2 is, right? So what I am supposed to get as derivative of x plus 2 is again 1, again 1, because it's parallel to y equal x, right? So we are going to see that. Okay. Now let's take y equal x square. That is the most important thing to understand, right? So let's take y equal x square, x squared, right? Now remember what we got as y equal x, derivative of y equal x squared. What we got is derivative of y equal x squared is 2x, right? 2x. Now let's see. Now this is 2x graph. Now remember this is the 2x graph, and this is the 2x graph, right? This is y equal x squared, right? So what this gives is the slope of the tangent. Slope of the tangent. For example, if it is y at 0, what is the slope of the tangent? The angle is 0. So therefore, what we get is 0. Right? Remember, I will write down the two functions again. So this is the most important thing, right? So no point memorizing, right? So let's say this is y equal x squared. Y equal x squared, or fx equal x squared. I will write it again. Fx equal x squared. So when you derive from the first principle, we got f dash x equal 2x. So that is why this line is 2x line. So you can see it's steeper. It's steeper. Now at x equal 0, right? If I put x equals 0 here, what I get is what? 0, right? Of course 0. At that point the rate of change is 0, right? But if I take uh, something like 1 here, right? 1 here, you can see, right? You can see that the rate of change is 2. Rate of change is, that means that this value 2, right? So of course, uh, at if you really draw a tangent at this point, you will find that this is 45 degree, sorry, not 45 degree, that tangent value is 2, that tangent value is 2, right? So if you take something like somewhat here, now you can see tangent is negative value, because it's a not a acute angle, it's an angle between 90 and 180. So you can see it's a negative values are also there. So that is why because the bigger angles, the tan value is a negative value. So likewise, at any time, if I want to find the rate of change, right? So look, this is the most important statement. If I want to find the rate of change at x equal, so let's zoom it a little bit, right? So if I want to find the rate of change at 4, what I am going to do? I have the derivative 2x. If I want to find the rate of change at say 4, I will not substitute 4 to here. I am going to substitute 4 to here. That means 4 into 2 is 8. That means at 4 rate of change is sorry, at 4 means sorry, at 2, right, this is x value, at 2 rate of change is 4. Why 2 into 2 is 4. 2 into 2 is 4. Now you can see at different point, if I want to find the tangent value, what I have to do is substitute that x value to this function derivative, that gives you the tangent value, right? So this height gives you the tangent value at different point, different point, right? Now let's take another one, something like x cube, right? So it's a little bit different thing. Now you can see you will find that the derivative of x cube is x squared. Now you can see this is x cube graph, this is x squared graph. Therefore, if I want to find the tangent value at this particular point, I have to substitute that value to y equal x squared. Then you get it. For example, I will give another example. So that you will find that, right? We say that when fx is x cube, right, you will later find that f dash x is 3x squared, 3x squared. Now if I want to find the tangent at x equal to or whatever, right, so what you have to do is don't substitute here, then you get the y value, substitute here, that is 3 times 2 squared. I want to find the value at 2, that is 2 squared is 4, 12. So answer is 12, right? Answer is 12. That you can find it from here also, right? So that is somewhere like here, point like here, and you will find that that value is somewhere to it. Okay, so that is what derivative is all about, right? So that derivative is the another function. So let's move to our note now. If you have a function, right, if you have a function, the derivative gives you the rate of change function. If you have a function, right, if you have a function, your derivative gives you the, it's another function. For example, if the function is x squared, rate of change is another function which is 2x, but it gives you the rate of change or the gradient of the tangent as the y value, as the y value, right? So that is very important thing to understand, right. So let's move on to another topic. Not every function is differentiable, right? Not every function is differentiable. It is differentiable only if it is continuous. That is obvious, right? So because you can't find a rate of change if it is not continuous, right? uh, right, you can find a rate of change at a particular whether it's a negative side or positive side, but you can't give a general rate of change value because it is not continuous at that point. Okay, so that is something you have to remember. So don't take it very seriously. For you, they are not going to check that, right? But there are situations you can't find a rate of change value, right? So those things are advanced things that we are not going to cover. Okay, right. So now we are moving to the now we are done the important part. right? So now we are done the important parts. Now we are moving to the trivial part that any fool can do, right? So now what I'm going to do is the thing that any fool can do. So what I covered is the people who have the courage, people who have the good attitude can understand. Okay, so now the things that any fool can do. So there are some derivative rules, right? We can use those rules to calculate some derivatives, right? Calculate some derivatives. So those rules we are going to use it, right. So the first rule is, if you have constant into function, you can just take out the constant and do the differentiation, right? Do the differentiation, right? For example, now already we found that, right? We already found that d by dx x equal 1, and also we already found that d by dx, first principle we found x squared is 2x. Now if someone asks you to find d by dx 3x, right? So this rule says you can take that constant out and just constant time do the derivative. So therefore I can take 3 out, and you can say d by dx x. Of course we know that d by dx x is 1, therefore the answer is 3 into 1, answer is 3, right? So similarly, if you have something like d by dx 5x squared, and now it's a constant, you can take it out, 5 times d by dx x squared. So we know that d by dx x squared is 2x, 5 times 2x, which is 10x. So that is how you apply this rule. Okay, that is how you apply this rule. Okay, so if you have a constant, you can just take it out. So that is the first rule, right? So we are not going to do the proof because it's beyond your syllabus, right? So you can just use those things. Of course, so far what are the derivatives you are aware of that we did using first principle? D by dx constant is 0, d by dx x equal 1. මේ දෙකම ඇගේ තියෙන්න ඕන දැන් d by dx x squared equal to x. So far we know only these three, right? So far we proved these three using first principle, then I gave you some examples for you to do. Okay, right. So the first rule says if you have a constant, you can take it out. So the second rule says if you have two summation of two functions, you can do the separately, you can do the derivatives, so differentiation and sum it, right? So that is the second rule. So for each one I'm giving examples. For example, here we say if I have find d by dx x plus 5. Now it's something like fx, something like gs. This rule says now you know how to find the d by dxx, you know how to find the d by dx5 because 5 is a constant. So this rule says you can just do the separately, do the derivatives and sum it, plus d by dx 5. Of course we know that d by dxx is 1 plus d by dx 5 is constant is 0, so the answer is 1. So you can see, you can use this concept, right? If it is something like x squared, we know that this is 2x, so the answer is 2x plus 0, right? So if the question is something like, now you can gradually start doing some questions. D by dx x squared plus x. Now with summation I can say d by dx x squared plus d by dx x. Of course d by dx x squared is 2x plus d by dx x is 1, the answer is 2x plus 1, 2x plus 1. So we can use these things. So similarly we have the subtraction also. If it is something like x squared minus x, so here just I have to subtract because for subtraction also it works. So it is going to be 2x minus 1, right? So now we have covered three rules: summation rule, subtraction rules, and the constant can be taken it out. Now we have two more rules: the multiplication rule and the division rule, right? Multiplication rule and division rule. So let's take those also. So far we only know these three, so we are going to add few more, but using these three we can understand each and every rule. Of course we are not going to give the proof because it's beyond your syllabus. So this is very fast I'm doing, because usually we do it very slowly. So first week we discuss about the first principle, second another gap, you are given a gap, and again we discuss about the rules, right? So likewise it's even in your A level, if you are doing A level maths, this calculus subjects span about 6 months, right? So they learn this throughout about 6 to 7 months, but you are going to do it in a, yesterday we did limits, today we are going to do the derivatives, maybe another day, next week or another few days time we are going to integration. So yes, I hope that you are very smart, you are smarter than A level students, because you are in a degree level. Okay, right. So the multiplication rule says, if you have d by dx f into g, f into d by dx x plus g into d by dx f. So how to remember this is, uh, first into second derivative plus second into first derivative. So that is how you remember it. First into second derivative of the second plus second into derivative of first. Okay, so let's so so don't think so those things will come go into your mind if you have understood the concept. Okay, so let's do an example. I want to do uh, something like, so we'll do some serious examples later. Again, when I say serious, these are any fool can understand session now we are in, right? Any fool can understand, right? So if someone can say d by dx sin x plus cos x is cos x plus sin x, don't take him as a very serious person. He's just one of the, even a fool can do that. So what the real genius people can do is explain what is the meaning of x squared, right? So using those plots, explain the meaning of it. So that is what the genius, or not genius, the even above average people can do, right? So any fool can remember saying that, okay, d by dx x squared plus c is 2x plus 1, because these are rules, just they have to apply. Okay, right. So anyway, so let's do that kind of things also. Let's take something like this, d by dx. So because I have only three derivatives yet, I can't do any serious stuff yet. Okay, so that is just bear with me, right? Say something like this, x into, or x squared. Now we know that x squared, derivative of x squared is 2x, but let's try to apply this rule, right? So I can write it like d by dx x into x. So just to demonstrate I am using this, otherwise you know that d by dx x squared is 2x. Now this is first function, this is the second function, fx dx. So what it says, first one into derivative of second one, and second one into derivative of first one. So just to make it interesting, I will make it x cube, then I will make it x and x squared, right? So x and x squared is x cube. Now I am applying this rule. Of course, now remember that we haven't done x cube, derivative of x cube. We know only these three, but now I want to find x cube. Okay, so I can write x cube as x into x squared. Now first one into derivative of second one plus second one into derivative of first one. So that is, this rule is all about first one, first into the derivative of second plus second into the derivative of first. So that is the multiplicative rule. Now we know that derivative of x squared is 2x plus x squared times derivative of x is 1, right? So what I got is 2x squared plus x squared, which is 3x squared. So that is the answer. Actually later you will find that yes, the derivative of x cube is 3x squared, right? So now without knowing derivative of x cube is 3x squared, we found it using these known things and the this multiplicative rule, right? Multiplicative rule. So that is how you do that. Okay, then we have the division rule. Division rule. So let's move on to the division rule also. Right, so division rule says, if you have f divided by g, it is g into df by dx minus f into dg by dx divided by g square. So you will see that it's weird thing, but don't worry, there is a way to remember this. Right, so don't think that it's very difficult thing to remember. No, this is how you understand. Uh, Below into above minus above into below. or down into up minus down into up derivative minus up into down derivative divided by down square. That is how you remember it, right? ඔබ සිංහලෙන් කියනවා නම් යට වාරයක් උඩව කලන එරින උඩ වාරයක් යටව කලන බෙදීම යට වර්ගය. හරි ඔන්න ඔය මතක තියාගන්න. ඔබ FG කියලා මතක තියාගන්න නැහැ. හරි. Right. So now let's do an example. Say I want to find the derivative of 1 divided by x, right? So we know x, right? We know constant because 1 is a constant, but still we haven't done 1 divided by x now. But I know this rule now. So it says down. Now look at how I am applying. This is down, this is up. Down into derivative of up minus up into derivative of down divided by down square. Down is x, x square. Now x, now we know that constant, when you derivative of constant is 0 minus 1, derivative of x is 1 divided by x square. So if this is 0, 0 minus 1 is 1. So the answer is minus 1 divided by x square. So we got that derivative of 1 over x is minus 1 over x square. So that you will find later also. So now we can see using these rules we can find different derivatives. We can find different derivatives, right? So that is good. That is good, right? Now we have covered these rules, right? Now we have covered these rules. Now so far we know only these three, but now using these three, now we can find some other things also by applying these rules. So I will do just one more example. Now I am using only these three derivatives that we proved, right? So we are not using anything for granted. We proved these three by definition, and we are using these three. Now we are doing some complex things, right? Finding the derivative of a complex thing, right? So let's say I want to find d by dx of x plus or something like this. X divided by x plus 1. So I want to find this derivative of this. So x divided by x plus 1, right? So the first thing what you have to do is you look at this as a quotient or division. So what is the division? This is my first one, x plus 1 is my second one. So this is my up one, this is my down one. So once you do some example, you will get it, right? So after some time you will find that okay, you can figure it out how to first look at the big blocks. So the big blocks are this block and this block. Now it's I can apply this division rule. So that means down into derivative of up minus up into derivative of down divided by down square. Down is x plus 1. Okay, and now I know that the d by dx of x is 1, right? So therefore I am just writing somewhere here x plus 1 into 1 minus x times, now this is a x plus 1, so that means f plus g, right? Because there are two functions x and 1. So what I can do, separately do the derivatives and sum it. So I can write it like this x into d by dx x plus d by dx 1, right? So then x plus 1 square, right? So then this is x plus 1. So I'm just going to delete this. Right? So from there I am going to come here x plus 1 minus x times d by dx x is 1 plus d by dx 1 is constant 0 divided by x minus x plus 1 square. Right? So let's simplify a little bit further. This is minus x and this is minus x. X minus x is 0. That is 1 divided by x plus 1 square. So that is the answer. Right? So derivative of x divided by x plus 1 is 1 divided by x plus 1 square. So let's see whether we made any mistakes. Down derivative of up 1 minus up derivative of this divided by x plus 1 squared, x plus 1 minus x times 1 plus 0 is 1 minus 6 plus 6 cancel it out 1. Yes, answer is 1 divided by x plus 1 squared. Now you can see using these rules we can now do some differentiations, right? So differentiations, right? Again, so don't worry about these getting these complex things. Ultimately what is this result is all about. So after some time what happens is you are doing a lot of differentiation, you don't know what is the result of this, right? Right, so that what is the ultimate result. So let's again get back, because you don't, that is the most important thing, right? That is the most important thing. uh, right, so let's get back to this. Right, so what is the most important point that you have to remember. So don't lose that, that is the most important thing. uh, so if you have some weird function, something, right, really complicate things like this, right? So let's call it fx. If you do the derivative of this, you get another function, right? You get another function, you get another function. It might be another weird function, right? So don't worry, don't worry. So this is the point that you want to get from this topic, right? So it can be another weird function. So if it is x squared plus x, it can be x plus 1. If it is x plus 1, x square, x cube plus 2x minus x divided by x plus 2 to the square, some weird thing. What you get is another something like that. Say it's another something like this, something like this. Right? So what does this means is, this is f dash x or dy by dx. Right? If I want to find the rate of change at this point, that means what? If you draw a tangent at this point, its gradient or its tan value, right? If I want to find this, what we are supposed to do? Is now you have got this one. Right? Now you have got this one. Come to this function. Right? Come to this function. Now, if you want to find this gradient at say x equal 5, don't substitute x equal 5 to this function, right? It can be something like x cube plus 2x plus x divided by x plus 1 or whatever. Here you will get some, when you using the rules, you will get another something like blah blah blah, okay, x squared plus whatever x or something like this. So what you are, if they ask you what is the rate of change of this function, and here now you got this one. Now you substitute 5 here, 5 here, so 5 square plus blah blah blah. You get something like, say, assume you got something like 30. Now you know that the rate of change of this function at x equal 5 is 30. So how did you find it? By first find the derivative of this, then you substitute this value to not this function, you substitute that value to the f dash x function or the derivative, you get the rate of change. So that is all about. So this is the most important point you have to remember, right? So that is why we want to find the rate of change or the derivative. If I want to find the rate of change here, of course, first I find the derivative of that. Then, if they ask you to find the rate of change from at x equal 10, I will substitute 10 here. I get the rate of change. So the tangent value, gradient of this one, I am getting as this y value. I am getting as this y value. Actually, this y value is the rate of change or the gradient of this tangent. Okay, so this is the most important point, right? The most important point. This is derivative, and this is derivative. But unfortunately, a lot of students, they cannot explain this. I don't know, right? So that means they are like calculators, right? Calculators. Now even the calculators are also smart. They are really dumb calculators. They don't know what is happening, right? So make sure that you know exactly what is happening. Okay, right. Now we are done with those rules. Also we have one more rule called chain rule that we will take later. Now what we are going to do is memory, right? So because when you are doing some maths as a math student, you are supposed to remember few derivatives, right? So then you are in any other math student, you are in the same you can work with them, right? So already we have discussed a few of those. So what are those things that we discussed? Derivative of a constant is a zero, that we prove using first principle. Derivative of x is 1, right? And of course we did what is that? Derivative of x squared is, right? Derivative of x squared is 2x, right? So this one we can generalize, right? This one we can generalize. We are not going to do the proof because we are running out of time also. D by dx xn, right? So this is just 2, n equal to, which is nx to the power n minus 1, nx to the power n minus 1. So mathematician found this pattern. So therefore if you want to do something like d by dx x cube, you can just say 3x squared, right? If you want to find d by dx x 100, you can say 100 x 99, right? So this n can be, it's very important, this n can be positive, negative, whole number or fraction. So for all scenarios this is valid. So therefore if you have something like d by dx x to the power minus 3, yes, you can do it using this rule, because even negative number it works. It is minus 3x minus 3 plus 1 is minus 2, right? Even when it is a fraction, d by dx x to the power half, right? Again half x to the power half minus 1 in minus, so half minus 1 is minus half, right? So that is uh, you know that if you want, you can take it as x and half. Okay, so that is how you do it. Now remember, when we were doing some examples, we get 1 over x. When we did 1 over x, d by dx 1 over x, we got it as minus 1 over x square. So how do we get it? D by dx 1 over x, we can write it as d by dx x to the power minus 1. So that using this x to the power nx rule, you can write minus 1 x to the power minus 2. So x to the power minus 2 is 1 over x squared minus 1 over x squared. Now you can see this is what we got using the division rule also. So same thing you can get it from the this rule also, this well-known derivative also, right? So this n can be positive, negative, whole number or fraction, right? So now we have covered a lot of scenarios, right? So now we have few things now. So we have this one and the generalized thing. So that means we know x to the power 3, x to the power 5, x to the power minus 3, x to the power half, whatever things are covered here. Okay, then so these things just you have to remember. The derivative of ex is again ex, and derivative of ex is again ex. So if you are not aware of what is Euler number, so you have to refer to that. We have done those things from your semester 1, right? What is mean by Euler number, right? So it's a very special function, something like this. If I remember correct, something like this. right? So the beauty of this ex is the derivative is also ex. So that is the only function that happens. For example, when you do the derivative of x, what we get is 1. When we say d by dx x squared, what we get is 2x. But when you have ex as the function, when you differentiate, you again get the ex. So that is a really unique feature of this function. So that is why when we take natural log, right? So remember we have the log 10 to base 10 stuff, right? 10, 5, whatever. Then you have ln or log e, right? So why we are interested about e is natural log is this ex is a really special, it behave in a real special way. When you differentiate it again you get the same function. So let's anyway demonstrate that also, because ex is a very you know that Euler number is a very famous, actually Euler number and phi are the two most famous, or the irrational numbers, right? Irrational numbers. So actually, I have uploaded a separate PDF called numbers for your Google Classroom. If you are interested about these things, you can read that small ebook and the numbers, right? So there I explain these Euler number, explain etc. Right. So let's look at this. So I'm going to delete this. Right. Now remember, when you have something like x, when you have something like x, what you get is 0, right? What we get is 1, right? What you get is 1. When you have something like x squared, right? So what we get is 2x, right? 2x, right? So this is 2x line, right? So when we have something like e to the power x, right? E to the power x, e to the power x, right? So this is ex graph, right? Now you can see, look at the differentiation graph. So that is the beauty. So you this graph and this graph is the same, right? So you can see. So it was not the case when it y equal x or y equal x squared or whatever. This is the only place where your graph and your derivative is the same graph, right? You can see if I want to find uh, the rate of change at this point, uh, I have to find the E2, right? So usually it is something else. You can see both are the same graph, right? So that is the beauty of ex function. That is why we take it as a natural log function also, right? So if you are interested about these things, read about these things, right? So of course if you are curious, right, if you like to think stuff, of course, right? But if you are sort of a gossip like person, politics like person, so you want to waste your time, you want to do some cheat other people, right? So like, right, so you want to just idle your life, right, find some money without doing any real work, of course don't think about that, right? Don't think about that. Especially countries like Sri Lanka, you have lot of opportunities to waste your life, right? Lot of opportunities are there to waste your time, okay? So use that opportunity, right? But if you are really interested about thinking, developing new things, right, of course understand these things, okay? Understand these things. So otherwise you can just waste your life, right? And be happy about wasting your life, right? Cheating other people, taking bribes, right? Taking some, right? So I'm not going to explain those things, okay? Right. So derivative of ex is ex, right? Then I'm just listing down, so you have to remember these things, because if you are a mathematical person, we expect you to know these things, right? Then only of course you are welcome to our maths club, right? The club of the mathematical people, okay? Right. Of course you have to understand the thing first, but we expect you to remember these things also, okay? So then the the derivative of ln x is 1 over x. So ln x means log e to the e to the base e x. So that is 1 over x. Then the log of, sorry, derivative of a to the power x is a to the power x ln a. Derivative of log ax is 1 over x ln a. Now remember this log, this is ln. Ln means log e. So those things you have to remember, right? So proof, of course we are not going to do it for you. If you are interested, you can see those things in the YouTube. Then we have some trigonometric things, right? So derivative of sin x is cos x, right? Then the derivative of cos x is minus sin x. Derivative of tan x is sec squared x, right? So usually if you are really interested about these things are naturally going to be in your mind, right? So derivative of sin x is cos x, derivative of cos x is minus sin x, derivative of tan x is sec squared x. Of course we can prove those things if you know, if you are aware of some advanced trigonometric functions. Since we are not doing any advanced trigonometric things for you, we are not going to prove it, but for those who have done A level maths, they know how to prove these kind of things, right? So sin x, proving that sin x is derivative of sin x is cos x. So for you, just remember these things, okay? Then derivative of cosec x is minus cosec x cot x. Derivative of sec x is sec x tan x. Derivative of cot x is minus cos x squared x. So if you can remember these things, of course you can see there is nothing much, right? Only about 3 6 7 8 9, so less than 15, less than 15, right? So if you can remember these things, you can do any of the derivative questions, right, in your paper also. So they are not going to check anything, they are not expecting anything other than this, not only from you, even those who have done A level maths, they are only remembering these things, right? So you know that mathematics is not about memory, right? So there are some professions, they heavily relying on memory, right? So because they know that any fool can remember things also, that is why they try to block enter into their professions also. I'm not naming those things, right? So they try to block enter into the profession because they know that any fool can remember things, right? So any fool can be my profession, right? So but it is not the case in maths. We don't relying on the memory, we are interested about processing, right, logic. So therefore if you can remember these set of things, that is good enough, right? This is good enough for your differentiation, because maths exams do not expect you to remember anything else, right? Anything else, this is the standard stuff we expect you to remember, just about 12, right? But when it comes to integration, right, so remember integration is the reverse process of differentiation. When you remember these things, you are remembering the integration related things as well, because later you will find that when we say derivative of ln x is 1 over x, we will say integral of 1 over x is ln x. Now remember, these things are investments. You are once you remember these things, you are remembering things for both derivatives and integration, okay? So when it comes to integration, you have to know three more things, actually six more things. That is, if you want to do the integration question, other than these 12, about 12 are there. So you better remember these things as well, right? Sine inverse x, derivative of sine inverse x divided by a is 1 over a squared minus x squared. Derivative of cos inverse x divided by a is minus 1 over a squared minus x squared. There is a small pattern. If you really look at it very closely, you will get the pattern also. Likewise, cosec inverse, sec inverse, cot inverse, and that's it. Nothing else, right? So just one page, just one page. I know that most of you are really good at remembering things, right? So try to get those things, at least these things, right? So then you are done with the differentiation. Very hardly they ask these things in the differentiation in your exams, but if you can remember these things also, you are in good shape to the integration as well, because integration is just a reverse process of differentiation, okay? Right, so now let's do some examples, right? So there are some examples given. I did a lot of examples with you, right? So I have given a lot of examples here, right? So I will do few examples with you, just a few examples with you. And so first I will write. So what I'm going to do is, I'm going to use these rules, okay? I'm going to use these rules. So that means I'm going to use these rules, okay? These rules. So I'm going to do those example right here, because then you can see the rules also, right? So therefore let's do it here. So just going to give you a few things, so you can do any number of questions you like. So assume that Now I'm going to use these things and those rules: summation, subtractions, division, multiplication. Those rules also I'm going to use. So let's take something like this: d by dx ex plus x, right? Ex plus x. Now I can apply the, I know d by dx ex is ex. I know d by dx x is 1. Now I know the summation rule. Therefore I know I can do it like this: d by dx ex plus d by dx x. And I know that d by dx ex is ex, plus d by dx x is 1. The answer is ex plus 1. So likewise you can do. So this is the easy part, right? So only thing is you just have to remember these things. So let's take one more example. Say you are asked to do this: d by dx uh, x, sorry, so let's do something like this: ex plus ln x. Now again summation, I can do it like this: d by dx ex plus d by dx ln x. We know that d by dx ex is ex and d by dx ln x is 1 over x. So the answer is this, right? Answer is this. So let's take just one more example: d by dx ax plus ex, right? So again summation, d by dx a to the power x plus d by dx e to the power x. So we know that d by dx ax is ax ln a and this is ex. So that is the answer. Right? So these are the simple things, right? So any fool can do things, right? So any calculator can do these things, right? Right. So now let's do some examples related to some trigonometric things also, right? So assume that you are asked to do something like this: d by dx sin x plus tan x, right? Again summation, I can do it separately: sin x plus d by dx tan x. So we know that d by dx sin x is cos x plus d by dx tan x is sec squared x. The answer is this. The answer is this, right? So let's do a something interesting one. Okay, so you are asked to do this: d by dx tan x, and of course we know that d by dx tan x is what? Sec squared x, right? So just double check whether it's correct. Assuming these two we know whether that is correct, and we are going to do something like this. So this is just for just to get things confirmed. I am going to write it as sin x divided by cos x, because we know that tan x is sin x divided by cos x, right? So now this is a division. So remember, division means below into the right, down derivative of up minus up derivative down divided by down square. So let's do that: cos x into derivative of up, which is sin x, minus sin x derivative of cos x divided by down squared cos squared x. So we know that derivative of sin x is cos x, that is cos squared x minus, so derivative of cos x is minus sin x, minus minus become plus, plus sin squared x divided by cos squared x. We know that sin squared x plus cos squared x is 1, that you learn in your trigonometry. That is 1 divided by cos squared x. 1 divided by cos squared x is means what? sec squared x, because 1 over cos x is sec squared x. Now you can see by using these two I can get that one also. So it proves that these rules are true. That is why you are getting always the correct answers, right? So these two rules are correct. So likewise, so let's do just one more example. So this is something that anyone can do, right? I am not going to spend a lot of time on this, right? So now let's combine. So assume that you want to do this, d by dx ex plus sec x. Right? Now I can do again the summation, d by dx ex plus d by dx sec x. So this is ex, some sec x derivative is sec x tan x plus sec x tan x. So that is the answer. That is the answer, right? So if you want, you can do few examples for sine inverse, cos inverse, etc. as well. For completion, just let's do just one of those. Right? So let's do it. So say you are supposed to do this derivative. D by dx sine inverse x divided by 5. So what is the answer? 1 over 5 squared minus x squared its square root. So that is the answer. Right? So then they might ask d by dx sine inverse x over 5, x divided by 5 plus cos inverse x divided by 5. Then you can add the summation rule. Likewise, you can do it. Okay. So those things I am not going to spend a lot of time. Those are the easier things that you can just understand. So these the most so again I am telling the most important thing is this one. So you have weird function like this. If you want to find the derivative, or if you want to find the rate of change at a particular point, find the derivative, then substitute that value to this one, you get a y value, right? So here you get a y value, right? Some y value, y naught. That y naught is the m, that m is that y naught. So that is the most important thing. So I keep on emphasizing, I keep on revisiting this because for me this is more important than just blindly. Of course you must have that ability to do differentiation using rules, but that is something you can build. No point building that unless you know that, okay, find the derivative and substitute that value, you get a y value. That y value is the m value, or the gradient of the tangent, right? So gradient of the tangent, okay, m equal this y naught. So this y naught, here you have to have x naught, you have to substitute here x naught, you get a value, that value is the gradient. Okay, so that is something what we are really interested about. Okay, right. So I have given you so many examples. If you find any issues, you can just ask in the WhatsApp group. Okay, WhatsApp group. Right. So again, if you want, you can keep this derivative again and again. So that is another interesting concept, right? So just like we differentiate it once, if you want, you can differentiate that rate of change value function again. So that is rate of change of that rate of change. So now remember, for example, if I have something like y equal, right, y equal x squared. Now you know that rate of change of this is dy by dx, which is 2x, right? If it is fx, oh, this is f dash x. So this is your function, this is rate of change of this. Now if I want to find the rate of change of rate of change, I can differentiate again. So we call it f double dash x, so f2x. That is d by dx, this function now, 2x That is, of course, you can take the constant out. 2 d by dx x is 1, the answer is 1. Right? So this is first derivative of this. This is the second derivative of this. So this is the rate of change of this. This is the rate of change of rate of change. Right? Rate of change of rate of change. So this is the rate of change. This is the rate of change of this. Right? So if this is something like time versus distance or the displacement, this is something like time versus velocity. This is something like time versus acceleration, because we know that acceleration is rate of change of velocity, right? So first derivative give you the velocity, second derivative, or the when you differentiate this one again, what you get is the time versus acceleration, right? So if you want to find the acceleration at a point, you substitute here, right? If you want to find the speed at point, you substitute here. If you want to find the displacement, you substitute here. Now remember, if you want to find the displacement, you substitute here. Say at t equal 5, substitute here. If you want to find the speed or the velocity at t equal 5, substitute here. If you want to find the accelerate at t equal 5, substitute here. Right? So that is why now you can build it to the next one, that is rate of change of acceleration, rate of change of acceleration. So likewise you can build it to any, right, to up to n. So that means you can keep differentiate again. Okay, so that is so that you can see it has a practical examples, right? Practical example. Of course, most of the time we are interested about this one, but there are situations we are interested about this one also, like we are interested about the acceleration, right? Not only the velocity, right? Right. So you get this kind of questions in the exam paper. So for example, if you have something like y equal, so if you have something like y equal x, right? Right. So you have something like y equal right, y equal x, sorry, y equal sin x, and we know that dy by dx equal cos x. So that is fx, this is f dash x. If I want f2x or f double dash x, I have to do it again, right? That is d2y by dx2, or cos x derivative is minus sin x. If I need f3x, I have to do another notation is d3y by dx3, that is minus, I can take it out, sin x derivative is cos x minus cos x. Again I can do this forever, right? So likewise, anyway you will encounter these kind of questions when you are doing some past paper questions. Okay, right, so let's do another practical example using this. Okay, so this is an example I have given you, which is in your note, student handbook from your UCSC. Right, so this is a very interesting example to understand, to apply your understanding. The distance s in meters an object moves in t seconds is given by st 120t minus 16t squared. So this is a time versus distance, right? Time versus distance, not the displacement. Time versus distance they are saying, but actually it will be displacement. Now you are asked to find the velocity after 3 seconds. Now remember, this is time versus distance, or time versus displacement. What you are asked to do is velocity after 3 seconds. You know that velocity is the rate of change of displacement. Of course, though they call it distance, it has to be displacement. It's the rate of change of displacement. Therefore, if you want to find the velocity after 3 seconds, what you are supposed to do is find the derivative, because that is where you get the velocity. Then substitute 3 in, not here. If you substitute 3 here, what you get is the displacement after 3 seconds, right? But if you want to find the velocity, you find the derivative of this and substitute 3 there. So what is the first step? So we have st equal, right, we have st equal 120t minus 16t squared. So what we want to do is we want to differentiate with respect to t 120t minus 16t squared. Then I can do these two as separate things, right? Summation rule or subtraction rule, and also I can take constant out. Then 120 d by dt t minus 16 d by dt t squared, right? So we know that d by dt t is d by dx x is 1, then d by dt t is 1. 121 minus 16 into 2t, so that is 120 minus 120 minus, sorry, not 12, this is 16. 16 into 2 is 32t, right? So our s dash t for the velocity function is 120 minus 32t, right? 120 minus 32t. Okay, so that is how you do that, right? So that is the first step, right? Now what they ask is velocity at 3 seconds. So now I can substitute 3 here, right? Is because what we need is the velocity, not the displacement. So s dash 3, that is 120 minus 32 into 3, right? You will get something like 24 meters per second, right? 24 meters per second, right? So that is how you do that. Now then they ask what is the acceleration after 3 seconds. Now we know that acceleration is what? Rate of change of velocity, right? So now what we have is the velocity function. This is the displacement function. I have the velocity function. Now they are asking about the acceleration. Therefore what I have to do? I am supposed to differentiate this again. Rate of change of velocity is the acceleration. So I am going to do this one again, differentiate, right? This one to get this double dash t, which is of course constant. If I differentiate, it is 0 minus 32 times differentiation of t is 1, what I get is minus 32. So that means my acceleration is a constant acceleration because it's always 32, right? Minus 32, minus 32 means actually it's a deceleration, right? It's not an acceleration, it's getting lesser and lesser, it's a deceleration. So not only at 3 seconds, at any time my deceleration is 32, right? So the answer is minus 32. So minus means it's not actually acceleration, it's getting the speed is getting lesser and lesser, right? The rate of actually not the speed, the rate of change of speed is getting lesser and lesser, right? So it's so at the speed is getting lesser and lesser, the acceleration is constant, minus 32. Okay, right? So next question is the time the velocity is 0. Now remember, this is my velocity function. So I want to make sure when this is going to be 0. So what I can do is I can just make it 0 and find the t value. Right? Make it 0 and find the t value. That is where your velocity is going to be 0. Right? So those things you can understand. Right? So just make it 0, then you will get the value. Right? Then they ask the distance the body has traveled before coming to reset. So remember, reset means your speed is getting 0. So speed is getting 0, we found the time. Then you substitute to this one and find the distance it has traveled. Right? Distance it has traveled. So that is something you can do. Right? Then the velocity after 5 seconds and the significance of sign. So you will get a after 5 seconds, if you get a negative value, that means it is coming towards you, it is not moving away. So you can see that it is actually minus 40, that means it is not leaving you, now it is coming back, because it's something like it goes like this and it is coming back like this. Okay, so think about those things, right? If you have any questions, you can raise those things in the WhatsApp group. Okay, right? So I'm doing it little bit hurry, right? But if you have any questions at any time, you can ask, right, in the WhatsApp group. What does this mean? Okay, so these kind of questions they rarely ask in your paper, right? But it's always nice to know these things. Okay, nice to know those things. Right. So the next topic is sketching the functions using derivatives. Right. Uh, so then we are done. Then we are done with derivatives. Right. So let's do that also very quickly. I know that this is a lot of burden or a lot of stuff doing in the same day, but I am going to upload this to YouTube. Therefore, you can again look at it. Again look at it and understand the things in a slowly. Okay, slowly. Uh, so let's try to understand that also, then we can finish the differentiation. Okay, then we can do the finish differentiation, right? So remember, in your O levels or whatever, now you have learned only two graphs actually seriously. That is the straight line, right? Straight line, something like this, and the sort of a parabolic shape, something like this, something like this, nothing else, right? So only those two you are interested, right? You never draw something like weird things like this, right? But since now we have the knowledge of calculus and the derivatives or differentiation, now we can start understanding these any weird shape. So that is another important tool that you get once you understand derivative, right? Not by memorizing. If you have understood the concept of calculus and especially the derivatives, now you can understand any of these shapes. So when you are given the function, you can guess, actually not guessing, reasonably you can sketch it. So sketch means not perfectly we are drawing, we just want to see the shape of it. That is what is meant by sketching, right? Sketch karna kila kya, right? Right. So for that, first we are going to understand few terminology, some words, right? So point like this is called a maximum, because now you can see it goes up and try to come down again. So this kind of points are called maximums. Okay, so I just draw it, right? So this kind of points are called maximums. This kind of points are called minimum, because you can see it comes down and it again goes up, so it's a minimum, right? Right. Then there are points like this, right? Something like this. It's like, so it's changed its shape, but it is not a maximum or minimum, right? It's not a maximum or minimum. This kind of points are called point of inflection, right? Point of inflection. So maximum, minimum, inflection, right? Inflection. So remember, we have three type of points now: a maximum, minimum, and point of inflection, right? Right. So what are those three type of points? Something like this, something like this, something like this, which is a maximum, something like this, which is a minimum, something like this, which is a point of inflection. So this can be of different shapes again. It can be something like this, it can be something like this, it can be something like this, or it can be something like this. So all these, right? All these points are point of inflection, right? Point of inflection. But what we are more interested is something like this or something like this. Okay, so everyone is interested about that, right? Everyone is interested about where is this point, where is this point, especially these days, right? Especially these days, for example, we are in the COVID issue, right? So what, who is, everyone is interested about when is it the peak point, right? Are we, have we uh, passed through the peak point, right? Still in the world, the moment that we are doing this uh, lecture, still in the world we are highly suspect whether we have passed the peak point. But in Sri Lanka, yes, we have, it looks like we have passed the peak point for this outbreak. Maybe there can be a second wave, right? So let's take an example. So you can see everyone is interested about this maximum, minimum, right? So those are called critical points. And now we can see in the world. So this is the the new cases. So what I want is something like, so let's take something like India, like India. So now let's see whether they have passed that maximum or whether they are still reaching the maximum. Now this is the daily new cases. You can see still it looks like they have not reached the peak, right? They have not reached the peak. It's getting increased, right? But now let's take something like Sri Lanka. So you can see that government is now relaxing in Sri Lanka, right? Of course, India also relaxing because they can't survive economic impact on the economy. So they are taking a lot of risk. But Sri Lanka, we are happily relaxing now. So let's look at Sri Lanka. So I'm more interested about these daily dates, not the accumulative value, right? So this daily new cases, so the active cases. Now you can see we had one maximum point here, right? Then it started to come down, but all of a sudden again it started going up, right? Again going up. Now we can see we have reached another maximum point. Now it's getting down again. So hopefully it will go like this. It will go like this, right? Because here also we hope that it will go like this, but because of this foreign people coming back from Middle East countries, again it start going up. Okay, so there's another point where these navy cases, right? So likewise, so we are interested about this point. So we are interested about this point because we want to take some decisions, right? So trend is changing. Trend is changing. Okay, but if you take something like India, the trend is pretty much going like this. Right? So pretty much going like the active cases are uh, keep on moving up, keep on moving up. So you can see one point there was a hope of going down, but again it's going up, right? Right. So that is why we are interested about these things. Huh? That is why. So that is why we have this graph to take the decisions, right? Take decisions, right? So this kind of a thing is called maximum. This kind of a thing is called minimum. These kind of things for four scenarios are called point of inflections, right? Point of inflections. So let's move on. Right. Then using derivatives, we can find where is a whether we have a maximum now here, whether we have minimum, whether we are increasing, whether the things are decreasing. Right. So if it is increasing, our derivative is going to be positive. Right. Remember, derivative is the rate of change or the tangent. So positive means it's tan theta is a positive value means it's a angle less than 90. So positive means angle is less than 90. So increasing means positive, right? Or positive means increasing. So our derivative value is positive means we know that we are in increasing situation, something like this or something like this. But if our derivative is negative at that point, we know that we are in something like this or something like this, right? So it's getting decreasing, right? So increasing means derivative is positive, decreasing means derivative is negative, or derivative is negative means decreasing, derivative is positive means increasing. So that is the first point you have to understand, because derivative is the tan value of the tangent. So tan value of the tangent is positive means it's a small angle, right? Negative means it's a big angle, right? A big angle more than 90. So that means decreasing, right? So that is the first point you want to understand, right? So by looking at that concepts, we can define whether we found a maximum or minimum. Right? Remember, positive means increasing, negative means decreasing. So if I have a situation where positive, zero, negative. So we had that kind of transition. Positive, zero, negative. We know that definitely we have passed a maximum. We have passed maximum. If it is negative, 0, again negative, that means we have passed a minimum, right? So we have passed a minimum, right? So why? Right? So it's something like this. It's negative, 0, positive, right? So negative 0 positive means we have passed minimum. Positive 0 negative means we have passed maximum. But of course, if it is positive 0 positive or negative 0 negative, what we have passed is a point of inflection, right? So it can be something like this, it can be something like this, it can be something like this, or it can be something like this. Now here positive 0 positive, here negative 0 negative, right? If this is this kind of a thing, we don't know which one, whether this one or this one. But if it is positive 0 positive, either this one or this one. If it is negative 0 negative, either this one or this one, right? So we can't say exactly which one, but either this one or this one. If it is positive 0 positive, if it is negative 0 negative, either this one or this one. But if it is positive 0 negative, definitely maximum. If it is negative 0 positive, definitely a minimum, right? But if it is positive 0 positive, some either one of these. If it is negative 0 negative, one of these. Okay, so by looking at this, so that is called the first derivative test. By looking at that test, we can see whether at that point whether we had a maximum, minimum, or point of inflection, right? Point of inflection. So that is very important, right? So identifying this turning point is the most important thing when we want to sketch a graph, right? When we want to sketch a graph. Okay, right? Then we have second derivative test also, right? Second derivative test also, that you can perfectly understand, right? So you can't say I can't understand this. If you have understood what is mean by derivative, what is mean by the gradient, you can perfectly understand this. If you have not understood, again put some effort, try to figure it out which one I am missing, right? So if you ask that question, of course I can help you, right? If you ask that question, I can really help you. Or else you have to again keep thinking. You must be able to 100% understand. Yes, positive 0 negative means maximum, and negative 0 positive means minimum. Positive 0 positive means either this one or this one, right? So this one or this one. Negative 0 negative means either this one or this one. Okay, so you just draw it by yourself and think about those things. Okay, so that is perfectly you can understand. Second one, actually you need little bit more thinking, that I am not going to cover, right? But I will just give you the test also. This is first derivative test because we are only looking at the first derivative only to find out whether it's a maximum, minimum, or point of inflection. In second derivative test, we look at both first derivative and second derivative, right? By looking at both, we are going to say whether it's a maximum, minimum, or point of inflection, right? So maximum means at that point. So here you have to look at the range. At that point, little bit earlier than that, little bit after that. At that point, little bit earlier, little bit after. At that point, little bit earlier, little bit after. So this is little bit more too much work. But when it comes to second derivative test, you don't have to look. You only have to look at only that place. So that is really easy for us. You just have to look at only that point. If at that point first derivative is 0 and second derivative is negative, we say that at that point it's a maximum, right? So just you have to look at that point, right? Here you have to look at that point, little bit earlier, little bit after, right? So that is too much of work. In second derivative test, at that point, if the derivative is 0 and the second derivative is negative, we know that it is a maximum. So anyway, I'm not going to do the proof because it's little bit advanced concept that I don't want to spend a lot of time here at this level. Then if that at that point, if the first derivative is 0 and the second derivative is positive, we can say that it is a minimum, which is a minimum, right? If it is a point of inflection, the both first derivative and second derivative is going to be 0. But unfortunately, in this case, we can't say exactly what kind of a situation, whether it's something like this, or something like this, or something like this, or something like this. The only point I can say is it's one of these four situations. That's it, right? So if you want to figure out what is the exact situation, of course you have to go for the first derivative test. But in these two scenarios, your second derivative test will tell you whether it's maximum or minimum, right? Maximum or minimum, just by looking at the first derivative and second derivative at that point. Okay, so that is how you those are the two tests. So either you can use the first derivative test or you can use the second derivative test. Okay, so let's take a very simple example. Let's take a very simple example. Say that I have a y equal x squared graph. Y equal x squared graph. You know that y equal x squared graph is something like this. Something like this. Right. So this is y equal x squared. Right. Now we know that at x equals 0 we have a minimum. So that is something we know, right? So let's see whether our theory is correct. Now I'm going to use the first derivative test. Right? I'm going to use the first derivative test. So that means first I have to find the dy by dx or the f dash x, which is 2x, which is 2x. Now let's see at x equals 0 what happens. At x equals 0 I have to find the derivative, right? So at x equals 0 this is fx, this is f dash x. Now you know that at x equals 0, my f dash x is what? 0. 2 into 0 is 0. So my f dash 0 is 0. Whenever I know that my f dash x is 0, I know that it's a critical point. So we call them critical point. That means it is either maximum or minimum or point of inflection. So that is the first knowledge I got. So if my f dash x is 0, that means I know that this is a critical point, interesting point. I am going to see a maximum, minimum or point of inflection, because you can see everywhere my dy by dx is 0, right? Now I know that okay, this is a interesting point. Then now I want to double check whether it's a maximum, minimum or point of inflection. If it is maximum, what will happen if I am only using the first derivative test? When it is little bit less than that, your f dash x must be positive. Now let's see. Now this is at 0. Let's take something little bit less than that. Now at 0 it is of course 0. Now let's take little bit less than 0. Let's take something like minus half. When it is minus half, what will happen? 2 into minus half is minus 1. Now you can see it's something like here it is 0. When it is little bit less than, it is negative, right? It is negative, right? So let's take something little bit bigger than 0. Let's take something like plus half or something like 1. So let's take something like 1. 2 into 1 is 2. 2 minus 1 is 1, which is positive. So let's take half. 2 into half is 1. Sorry, not 2x, 2x minus 1, it is 2x, right? So let's take something a little bit bigger than 0, right? Because 0 is a critical point. So 2 into 1 is 2, so that is positive, right? That is positive. If you take half, 2 into half is plus 1, that is positive. If you take 0.1, 2 into 0.1 is again positive. Now you can see it's minus 0 plus. So minus 0 plus means what? It's a minimum. So we know that at x equals 0, we are going to see a minimum. So that means I can draw something like this, right? So for y equal x squared graph, now I definitely know that at x equals 0, I have something like this. I have something like this, right? Because I got it from the first derivative test. First derivative test. Okay. So let's take another example. Right? Another example. Let's say y equal x cube, right? Y equal x cube. So let's move to this one. I'm going to delete this, right? So let's take y equal x cube. Y equal x cube. Now first I'm going to use the first derivative test. Dy by dx. So the f dash x is, this is fx. F dash x equal 3x squared, right? So by rules. Now we know that when x equals 0, this is 0. That means yes, x equals 0 is an interesting point, right? X equals 0 is an interesting point, right? So there's something going to happen there, because there dy by dx is 0, right? It is going to be something like this, or point of inflection. So there are four possibilities, right? Now what I'm going to do, I'm using the first derivative is I'm going to use something little bit less than 0 because my critical point is 0. Something less than 0 and see whether it's positive or negative. Say something less than 0, something like -1. -1 squared is +1. +1 into 3 is +3. It is positive. Right? So now you can see positive. Right? Now so -1 squared, right? So now let's have something like +1 because it's little bit bigger than 0, right? So +1 squared is +1 into 3 is +3, that is again positive, right? So not only +1, if you take half, any number square is a positive number, positive into positive is positive. Any negative number square is a positive number, positive into positive is positive. Now you can see this is a positive 0 positive scenario. So if it is positive 0 negative, we know that is the maximum. Negative 0 negative, we know that it's a minimum. But if it is a positive 0 positive or negative 0 negative, we know that is a positive 0 positive means it's something like either this one or something like either this one, because it's negative negative means something like this one or something like this one. So what we have is either this one or this one, but I never know whether it's something like this or this one. Okay, so that you need some more theoretical aspect to do that, but at least I know I am going to see something like this or something like this at x equals 0. There are no other point where x is going to be 0, therefore that is the only critical point. So this x equals 0 is the only critical point, okay, for y equal x cube graph. Okay, so it must be either this one or this one, I never know. So it can be something like this or something like this. Now let's really look at the exact graph y equal x cube using our online tool. I'm just going to delete this. Right, so let's hide this. So let's plot y equal x cube. Right, now you can see something like this. Now you can see that positive. Right, so you can see positive 0 positive. Right, positive 0 positive. Right, so if you look at the derivative graph also, positive 0 this is positive. Now you can see y value is positive 0 positive. So positive means the y value here, right? Here, right? Positive 0 positive. If you look at the gradient, positive small angle 0 again small angle, right? Again small angle, right? So positive. So in that case it happens to be like that, but there can be a situation where it's something like other shape also. But if you when you take y x equal y square, it was a different scenario. Right, now you have the negative bigger angle, right? Negative 0, right? Now all of a sudden it becomes 0. Now again it's positive, right? Negative 0 positive. Now here also you can see negative 0 positive, right? Negative 0 positive, right? So if you can think, this is something seriously interesting thing for you to think, right? So this is that is how you have a lot of fun using math, right? So you will get a lot of satisfaction, right? So I understood something really weird mathematical concept, right? The concept of differentiation, so that will give you a lot of satisfaction, and of course that will give you a lot of confidence, right? So when some people say no I can't, it's too complex, I don't understand, you will say no, no, I can understand this, I can handle that complex thing, I can develop that software, I can figure it out what is that error is, right? I can build that. So remember, in Sri Lanka we are really terrible at doing complex things, right? So we are really terrible at complex things. We are really good at doing cheating, right? All sort of bad things, right? So but we can't even create a highway. So Chinese people has to come here and do the highway. Chinese people has to come here and build all the high rises, right? They are doing the port city and they build the harbor, right? So they are doing all those big complex things, right? So why they don't know what is the fear is, right? They don't know what is the fear is. They know how to tackle complex things, right? Even the European people, right? But the Sri Lankan people and Indian subcontinent, African people, they are not good at handling complexities. So try to get out of that mindset. Right? Try to get out of that mindset. Try to understand these things. Okay, right. So I didn't do it in a very slowly. I did it in a little bit faster, but you must be able to do those questions. Anyway, next time we are going to do some past paper questions. Again, I will explain these things, right? So actually I'm going planning to do it this maybe tomorrow or day after tomorrow, the past paper session. There I will be again revisiting this. Okay, right? So I think so we are done with that, right? So now hospital tool rule I am going to do it separately, right? So that's why I'm going to separate basically now we are done with the differentiation. Now we are done with the differentiation. So we start with the definition, what is derivative or the rate of change function, then how to find it in using the first principle, right? Using this graph. Then we discuss some well-known derivatives and also some rules, summation, subtraction, etc. So only rule I didn't do is the chain rule. The only rule that I didn't do is the chain rule that I am going to do in the next session. So that remember we covered 4 rules and skip one of the rules. Right? We skip one of the rules. Right? So we did 1, 2, 3, 4. We did all these 5 rules, but I didn't do the chain rule that I am going to cover in the next session. Right? In the next session when we are doing the past papers. Other than that, everything is done. Other than that, everything is done. By the way, anyway, I will just because then you can start doing the past papers. I will briefly explain what is chain rule also, then stop it. It will take another 5 minutes only. Right. So the chain rule says something like this. Right. So this is a very interesting rule, chain rule. Say now remember we did questions like this. If we want to find something like this, d by dx uh, sin x plus ex. Of course, you can do the summation rule. You can say d by dx sin x plus d by dx ex. So we know that d by dx sin x is cos x plus d by dx ex is ex. Okay. But if you get something like this, so now let's take another example. D by dx ex sin x. Now it's a multiplication. So how to do the multiplication? First into second derivative plus second into first derivative. Ex d by dx sin x plus sin x d by dx ex. Right? So we know that sin x derivative is cos x plus sin x times derivative of ex is ex. So if you want, you can just take ex out, factor. You have sin x plus cos x. That is your final answer. Right? But there are situations where you have to use this chain rule. So don't look at this chain rule. It's a weird rule. Just look at the examples only. Right? Then you will understand what they are talking about. Okay. Right. So let's take the chain rule. So I'm just going to do a simple example using chain rule. Using example, I'm going to explain what is meant by chain rule. Okay. Say you want to find this d by dx. You want to find something like this. X plus 1 its square, right? X plus 1 its square, right? So you don't know what is x plus 1 square, but you know what is x squared, what is 2x, those things you know, right? And also you know what is mean by d by dx x squared, that is 2x1 because xn is nxn minus 1. What you can do is right, so look at closely. So what I need is d by dx x plus 1 square. Right? So remember that is what I need. I don't have a rule for this, but I have a rule for x to the power n, nx n minus 1. So what you are going to do is you think of this as just think this x plus 1 as x. So if you just look at it, all of a sudden it will become 1 d by dx x square. Right? You know that d by dx x squared is 2x because xn is nx n minus 1. So look at what I am doing closely. I am using the chain rule. I am just thinking of x plus 1 as x. You can think, right? Then you see it as x squared. So derivative of x squared is 2x. What I think as x is x plus 1, right? So because that is 2x, right? If you look at it like capital X, 2x, but capital X is x plus 1. But what you have to do is that is why we call it chain rule. You have to multiply it by what you think as your x. So what you think as your x is x plus 1. You have to multiply it by the what you thought as your x, right? So then the final answer is, of course, this one is d by dx x is 1, 1 plus 0 is 1. So the answer is this. Right? So that is how do you use the chain rule. Right? So at first it look weird, but once you do few example, you will get it. So let's do another example. Okay. So because then you can do any past paper question. Right? So that is why I'm going to do the chain rule. Any differentiation related question. Right? So let's say I want to find e to the power sin x. So it looks like very weird, but what we are going to do is we don't know what is e to the power sin x, but we know what is e to the power x. Derivative of e to the power x is e to the power x. So therefore what I am going to do? I am going to think of the sin x as x. Think of it, right? Think of it. Then all of a sudden what I see is e to the power x. So what I know is e to the derivative of e to the power x is e to the power x. Right? So therefore I am going to say e to the power x, but that x is what? Sin x. But right, so what I thought as x is sin x, I have to multiply it by what I thought as x. What I thought as x is sin x. So that is why we call it chain rule. Right? Now the final answer is e to the power sin x. We know that derivative of sin x is cos x into cos x. So that is your answer. So likewise, complex things now you can do using chain rule. Right? So again, proof is not given, but you can use it. Right? You can use it. Even the proof is not given even for your A-level students, A-level math students, right? Because it's little bit complex proof. Right? So let's take one more example. Assume that you want to find something like d by dx uh, ln ln sin x, and this is ln of sin x. Okay, now again I don't know what is ln sin x, but I know derivative of ln x is 1 over x. So what I am going to do is I am going to think about sin x as x. Then all of a sudden what I see ln x, right? So if I imagine this as x, what I see is ln x. Derivative of ln x is 1 over x. Therefore I am going to write it like 1 over x, but that x is sin x. What I thought as x is sin x, therefore I have to multiply it by what I thought as x, which is sin x. Right? So now 1 over sin x, I know that derivative of sin x is cos x. If you want, you can subdivide and say cos x divided by sin x is cot x. So that is how you get it. So I will just one more and I will finish the session, because chain rule is very interesting and very important thing. So if you have something like this, d by dx uh, x to the power x to the power, so let's take something simpler, x to the power ln x. Okay, so let's take something like this, uh, ln x, so something like this, ln ex. This is what I want to do, right? I want to differentiate ln ex. I know what is ln x, but I don't know what is ln ex. So what I am going to do, I am going to think of this ex as x. Then it is all of a sudden ln x. So I know that 1 over ln ln x, the derivative is 1 over x. 1 over x, but what I thought as x is ex, but I want to multiply it by what I thought as x, that is ex. Right? So I know that derivative of ex is ex, that is ex divided by ex, which is 1. So answer is 1. Now let's see whether that is correct. Right, now you know that when I say ln ex, it is log e to the base ex. So that value is basically x. So this is same as derivative of x, and we know that derivative of x is what? 1. Yes, that is what we got, right? That is what we got. So actually when I say ln ex, what I have written is basically x, right? What I have written is basically x. You know that derivative of x is 1. Yes, that is why using the chain rule also I got it as 1. Okay, right. So I'm going to stop at this point. I did a lot of things, right? So if you have any questions, you can ask those questions in the WhatsApp group. Okay, right. Thank you.